Let's get that going. And let's quickly remind ourselves with what we ended with last time in chapter 7. The last couple of theorems we proved that will come up a couple times was, first off, the one with exterior angles. So if we have a triangle, some triangle ABC, we call this angle right here an exterior angle to that triangle, and we proved that an exterior angle is larger than either of its interior opposites. This angle is bigger than this angle, and this angle is bigger than this angle.
Right.
That's one important thing that we proved last time. The other thing that we ended with was the triangle inequality.
Right.
Which said in any triangle, if I have triangle ABC,
AB plus BC is greater than AC.
then it's always and forever the case that the length of AB plus the length of BC is always greater than the length of AC.
Yeah,
The length of AC. Okay, so those were two things that we ended with proving last time. Now we're going to do a slew of definitions before we get to RC constructions. So our first definition is what is called a polygonal path. A polygonal path. What's a polygonal path? Take some points. Here's point P sub 1. Here's point P sub 2. Here's point P sub 3. Dot, 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 dot. Whatever. All the way to P sub n. Polygonal path, if we connect all these with line segments, we call this a polygonal path. So we call that a polygonal path. We call these points P1, P2, P3, dot, 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 the vertices of the polygonal path. And we call these segments the edges of the polygonal path.
Okay.
We call the length of the polygonal path the length of that plus the length of that plus the length of that plus the length of that, da da da. Pretty intuitive.
Yeah.
We get an instant corollary from our triangle inequality from this. That is that the length from P1 to Pn is always going to be less than or equal to the sums of all these different lengths. It's going to be less than the length of P1 to P2 plus the length of P2 to P3 plus dot 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 plus the length of P of n minus 1 to P of n.
You're saying a straight line from P1 to Pn.
Right. So the blue line I'm about to draw is shorter than doing the polygonal path.
Right.
And we get that from the triangle inequality.
Shorter than or equal to.
Less than or equal to. Could be equal to. Because all those points could be perfectly collinear
Straight line.
points. It could be a straight line. Or they could all be in a line. Now how do we instantly get that from the triangle inequality?
Because the length, the one, I think the proof one literally said just that.
We can always cut out a middle point really quickly. So I know, for example, look at the polygonal path I have right here. I know that if I cut out this path and go from here to here and cut out that part, I made it shorter.
Right.
Now cut out this point too, or now cut out this point and go straight to here. So look at how I had a triangle here. I made a triangle.
Right.
I said this is shorter than going that. Okay. Well, we can leave that. And now going straight to here. Now this triangle, or going to here, is shorter than going that. And cut out the next one, cut out the next one. You know, each step of the way, you're making the path a little bit smaller. And so when it's all said and done, you're left with a smaller path. We need to prove that inductively. If we were to prove it, you don't know proof by induction yet, so we're not going to do it. It's not a hard proof technique, just not something we're going to delve into.
Okay.
But that's the big idea. So that's polygonal paths. Now we have a polygon. What is a polygon? A polygon is a polygonal path that starts and ends at the same point. So let's say this is P sub n minus 1, and then finally, my last point right here, this is P sub n. So let me shoot off up like that. So if your path starts and ends at the same point, then we call it a polygon. That black is down. Okay? Polygon. We call it a simple polygon if none of the sides, none of the edges intersect each other.
So
Notice how this edge intersects this edge right there. Sheesh. Are all these dead? So this is not a simple polygon. Let me draw a simple polygon for you. Here's a simple polygon.
Does a polygon have to have a certain amount of size?
Does a polygon have, it has to be a polygonal path that starts and ends at the same point.
So a square is a polygon.
So a square is a polygon. Any shape that you're used to calling a shape is a polygon. So here's a polygon. This one's a simple polygon because none of its edges intersect themselves. This one is not a simple polygon.
But it is a polygon. But it's
It
not.
is a polygon.
How? Doesn't the polygon have to be enclosed?
A polygon is a polygonal path that starts and ends at the same point. This is a polygonal path that starts and ends right there.
Oh. You're saying it goes to P.
Yeah, it goes,
Nine,
there's P1 to P2 to P3, P4, P5, da 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 da, P sub n minus 1, P sub n.
Okay, so it intersects.
And it has an intersection point right there, and so it's not simple. This one is a simple polygon. For simple polygons, we have a notion of their interior and their exterior. 2 points are in the interior of a polygon if I can connect them with some polygonal path that doesn't intersect our initial polygon.
Wait, say that again.
So here's some polygon, some simple polygon. Are these 2 points both in the interior?
Yes.
So both points are in the interior, or both points are in the exterior, if and only if I can create some polygonal path from this point to this point without intersecting this polygon. One's in the interior, one's in the exterior. If every polygonal path between them has to intersect the polygon.
Right,
Okay.
the one on the interior can also intersect the polygon.
So here we said, if every path intersects the polygon, then one's in the interior, one's in the exterior. Here we say, if you can find a single polygonal path between them,
Okay.
then they're both in the interior.
And they don't intersect.
If you can find a single polygonal path that doesn't intersect the polygon,
Then they are intersecting in their interior.
then they're both together in the interior, or they're both together in the exterior. If every polygonal path intersects the polygon, then one's in the interior, one's in the exterior.
So that's how you prove.
We won't be doing proofs with points in interiors and exteriors of polygons, but
Okay.
just going over a bunch of definitions. Okay, that was a simple polygon, convex polygon. This is kind of a convex.
Okay, so like complex with a V.
Convex as in the counterpart to concave. Concave and convex. No? No.
Never heard that before.
Alright, well, now you agree. So here's one. Here's another. This one is convex. This one is not. What's our definition for convex? In short, it's our way of saying all the angles are somehow nicely behaved. That's intuitively what it means. What's our precise definition for it? Our precise definition for it is for any 2 points you pick on the polygon. Remember, on the polygon is the actual path.
Right.
This is not a point on the polygon. This is not a point on the polygon.
Right.
This is.
Okay.
So a polygon is convex if and only if for any 2 points you pick, they can be connected by a line segment that does not intersect the polygon.
That's a convex polygon.
So if it's convex, then that's the case. So this is not convex. This says pick any 2 points you want, draw the line segment between them,
Right, because the line segment.
and the line segment does not intersect the polygon anywhere between those points. Over here, it does. So convex, not convex. So in general, we work with simple convex polygons.
So is that, you call it a simple?
This is
What do
still
you call the
simple.
one on top? That's simple?
It's still simple. This one is both simple and convex. And typically we're interested in simple and convex ones.
So what do you tell the top? What do you call the top?
It's a simple polygon.
That's it, you don't call it concave or whatever.
I'm not sure if they use that terminology ever, but you say that relative to curves? I don't know with polygons. Either way, so there's a simple one. And then finally, well, there's a few other things. If all its side lengths are equal, then we call the polygon equilateral. That means all sides are equal.
Right.
Okay, there was a question on the homework about that. I was kind of confused. About, it was proving an equilateral triangle using theorem 6 or something.
Proving an equilateral triangle is isosceles. Is that it?
No,
I know that's probably it. We did that one.
Yeah, I think we did that one in class.
oh, did you?
Yeah.
Okay, so that is an equilateral polygon. If all the angles are congruent,
It's an equal angle.
then it's an equal angular. So we have equilateral shapes and we have equal angular
It's
shapes.
just like triangles.
If it's both equal angular and equilateral, we call it a regular polygon. So when you imagine a hexagon in your head, chances are you think of a regular hexagon or a regular pentagon.
Or regular octagon, whatever it is. Right.
Yes, and then we have our basic names for them. Notice that polygons start at
Fine.
3 sides
Triangle.
with a triangle.
Wait,
So
so a circle wouldn't be a polygon?
we think we'll get to how we can think about circles as a polygon. That will be a couple chapters down the road. But intuitively, we think about a circle as an infinitely sided polygon. Not no sides, infinite sides.
Infinite sides.
Right. That makes sense
Instead
because
of one
there's,
side or?
because triangles are so, the sides are so short that it just sort of.
Yeah, we'll get to how we can think about a circle that way. But for now, when it comes to these polygons, we have the simplest one we can make is a 3-sided polygon, which we call a triangle.
Then a square.
Then, not a square, what do we call a 4-sided polygon in general?
Rectangle.
No, there's rectangles, there's squares, there's a rhombus, there's just parallelograms.
Oh, it's oh.
Oh,
Man. No.
It's got to be tetra, right?
Tetra?
Isn't that
I think
high?
they have it listed out somewhere. A tetragon?
Never heard that
Triangle. No, what is it?
Isn't it
Quadrilateral.
quadrilateral?
Quadrilateral. There we go.
I was
They don't
gonna
use
say-
tetra. Okay. Quadrilateral. So triangle, quadrilateral. Then we get pentagon, hexagon, heptagon, octagon, nonagon, decagon. Then it's going to be the same as like organic chemistry.
Tetragon.
before. Tetragon?
Sorry. Tetra. It's another word for 4. Trying to remember the one that they used in geometry. It's quad. They use quad. Okay.
Quadrilateral.
So it's a quadrilateral.
Quadrilateral or quadrangle?
It is a quadrilateral. That's what we call it. 4-sided. Equilateral means equal side. Quadrilateral means 4-sided. So some of the ones that we use a lot, they might have special names. They don't follow the pattern. And then when it comes to just regular pattern. So from 5 onwards, it's just a pattern of penta, hexa, hepta, octa, nona, deca. Hept.
7.
H-E-P-T. Hept 7. Yes.
Octa is 8.
Oct is 8. Non, N-O-N, 9.
9.
And then dec, 10. Yeah.
Decimal.
Okay. Anyways, so what else did we need to talk about with polygons? I think we pretty much covered it. Some of the basic shapes, let's understand what they are. What's a parallelogram?
All 4 sides.
No,
all
the
4
two sides are.
The 2 pairs of sides.
At
All
least
sides
two
are-
sides.
It's a quadrilateral where both sides are parallel to each other.
So it has to be quadrilateral. You can't have a parallelogram that's a octagon.
We're always talking about a quadrilateral with a parallelogram. So something like that, parallelogram. What's a rhombus? A rhombus is a parallelogram where all the sides happen to be the same length.
So what's the one
So a
that's like
square is a rhombus.
A square is a type of rhombus.
this? So what's the one that has the sides tipped in?
That's just a trapezoid.
Trapezoid.
A hexagon, if all the sides are equal,
We don't call it a parallelogram.
we call it an equilateral, right?
Yes.
So we're going, this is just an equilateral. equilateral, but for only
A
four
rhombus
sides?
is equilateral for four-sided.
Okay.
It's an equilateral parallelogram. Now, I think if you have your sides equilateral, then you automatically have a parallelogram. I think that there's a way with four sides to have it equilateral, not a parallelogram. Okay, so rhombus. Let's see, rectangle. What's a rectangle? It's a parallelogram with a right angle.
Why do you say with the right angle?
So this is a parallelogram. It
It's
is
not a
not a rectangle. If I force it to have a right angle, so there's a parallelogram, but I gave it a right angle.
So it's rectangle.
So now it's a rectangle. And then you can think about a square as an equilateral rectangle, or a rectangle rhombus, or however you want to think about it. But a square is a rectangle, but it has all four sides equal.
Can you have a parallelogram where do the reflecting sides have to be the same length, or can a side length and a top length be the same length?
In a parallelogram,
That's impossible.
then opposite sides are going to be the same length.
They have to be.
Opposite sides have to be the same length because in order for it to be parallel in our geometry, the lines have to be the same distance apart. And so if you try to make one shorter, you're going to pull the lines in some.
Right. I mean, if this side was the same as this side, then these things will not be at 90 degree.
Yeah, but it doesn't have to be at a 90-degree angle. A rhombus isn't at a 90-degree angle.
Right, then it's not a parallelogram.
Yeah, it is.
Yeah,
Oh.
you don't need a right angle for a parallelogram.
Right, but here's what I'm saying. If this length is the same as this length,
That's a parallelogram.
no, we say the side length is the same as the top length, but the other two lengths
Yeah.
aren't the same.
So this length is the same as this length.
No, side length.
Okay.
It's impossible.
So this length is the same as this length.
No.
No.
That
I'm
length is the same as
saying,
the top
can
length.
a side length.
So these two are the same?
Yeah.
Yes.
Is that a parallelogram?
So if those two are the same length, does that force this thing to suddenly be a parallelogram?
No.
And the answer is no, because I could extend this out like that, and I could shoot this out like that. This is in no way parallel to that thing.
See what I'm saying?
That's a what? I didn't hear.
This is not parallel to that anymore.
Oh,
It's not forced to be a parallelogram.
if you can extend it in any way to.
Yeah, let's see, you draw the shape. Put what you have required. Now see if you can break it from there on out.
But you can't. Very easily.
But you can. Okay, now we get to our definition of a circle. I told you we'll come to it later how we can think about it as an infinite polygon. That's not going to be our definition. What's our definition of a circle? Given some number r, so r is a number, like 5,
Radius.
AKA radius.
and given some point O,
From O to the rest of the thing.
then the circle is a set of all points A such that the distance from O to A is equal to r.
Which we like to call the radius, right?
Yes.
All the way around.
Basically,
Sometimes,
that's-
every point. So this point, its distance from O to this point is
Better be
r,
R.
so it's on the circle.
Better be R.
So
It's
this
not R, it's not
is
circle.
on the circle. If the distance from O to A is less than r, then we say it is in the interior of the circle. And if the distance from O to A is greater than r, then we say it's in the exterior of the circle.
Okay, what would that diameter be?
Well, let's understand this first and then go from there. So pick a point A. My r is 5, and we'll pretend that 5 is this length right here. So this right here is a length 5.
Okay.
So pick a point A. If distance from O to A is greater than 5, we say that A is in the exterior. If we picked A here, and the distance from O to A is less than r, then we say it's in the interior. And if we picked A here, so that its distance from O to A is exactly r, then we say A is on the circle. Important point, a circle, like a polygon, is just actually the point right here. This is not a point on the circle. Sometimes we think about circles like discs. Circles aren't discs. Two different things.
Right, what do you mean?
A disc you think of as solid. This is, if I was drawing a disc, that's pointing at a disc.
Yeah.
So difference between circles and discs. Okay, now the radius of a circle. If A is a point on the circle, then we call OA the radius of the circle.
This is equal to R. Wait.
If a point is on the circle, then we call the length, we call the segment OA a radius. Now, you've already noticed some ambiguity. R, strictly speaking, is not the radius of the circle. R is the length of the radius of the circle. A radius is a geometric figure. That is a radius.
R is 5.
R is a number. R is not the radius. We will often speak loosely and call R the radius and call a number the radius.
R is the radius.
But strictly speaking, understand that R is really a segment. A radius is a segment. We will loosely say, let's look at a circle with a radius of 3 and pretend like a radius is a real number, but strictly speaking, it's not. So it's usually obvious what we're talking about, but just to be
You're
clear,
saying a radius is just a way of measurement.
I'm saying that if you have a circle, center that up, and you pick a point on the circle A, then this segment is a radius of the circle. This segment is also a radius of the circle if I drew it in. There's infinite radii.
It's also R too.
Its length is R. OA is our segment. OA is our radius. The length of OA is equal to R. So R, strictly speaking, is not our radius. It's the length of our radius. But we will loosely call it our radius. And you just need to understand that when I say the radius of this circle is 5, what do I really mean? I mean, if you were to take a radius and look at its length, the length would be 5.
So you can say the length of the radius is 5.
That would be a more proper way to say it. Let's look at a circle such where the length of the radius is 5. That's a more proper way to say it, but no one really bothers spelling it out that way. And then finally,
The R of the radius is
if you take 2 points on the circle, if you take 2 points on the circle and look at the segment between them,
Such that they intersect O.
take any 2 points on a circle. So here's one scenario, here's another scenario. A, B. And look at the segment between them. We call this segment a chord. We call it the diameter if it happens to go through the origin. So if O is between A and B, we also call it the diameter.
But it's also a chord.
It's always a chord. This is a chord, this is a chord. A diameter is a special type of chord. If you look at the line that goes through the chord, so AB, if we look at the line that goes through it, we call that line a secant line, just terminology. If we have a point and we look at the line that goes through that, just that point and no other point on the circle,
Tangent.
we call that a tangent line.
What do you call the one that AB is short? A sequent?
That right there is a chord.
That's a chord, but what about the line that goes through that?
The line that goes through it is called a secant.
Secant?
Secant. As in, when you get to trig functions, exactly what the secant trig function is getting its name from.
diameter is secant too.
The line through it is a secant.
Secant?
Yeah. Just terminology. Let's see, what other terminology do we need from the circle? So radius, diameter, most of these words you're already familiar with.
Yeah.
Circumference?
Circumference, I don't know if we're getting to circumference yet because we haven't talked about the lengths of arcs.
Of the degrees yet?
Well, angles, but also, we got something weird going on here. We've got these arc things.
Yeah.
We're used to talk about lengths of straight segments, what we call straight.
Right.
So we've got something different to deal with there. So I don't think we do circumference yet. Let me just
When do we start?
look at our definitions. Chord, circle, oh, central angle and inscribed angle. Those were the last time missing.
When do we start getting into degrees and stuff and measurement systems?
Measurement of angles, I think it's like chapter 9. Okay, finally we have a central angle and an inscribed angle. So what's a central angle? So I have got some circle with its center O. As a general rule, we use O for the point in the center of the circle. If the angle has its vertex at O, we call it a central angle. So here's an example of a central angle.
Okay.
Okay.
We call it an inscribed angle if the vertex is somewhere on the corner, if the vertex and each of the angle's sides intersect the circle. So I have to have the vertex on the circle, and when I draw the sides of the angle, the sides have to also intersect the circle. This is called an inscribed angle. So we're looking at this angle right here.
Okay. So the side can't land on the.
I couldn't have had this other side shoot out like that. That is not an inscribed angle.
It has to intersect.
Both sides have to intersect the circle, and the vertex has to be on the circle in order for it to be an inscribed angle.
I'm saying the two sides can't land directly on the circle, or does it?
How does it land directly on the circle?
On the.
You're saying it shoots off like this?
That's the vertex. I'm saying this side, right there.
So this side right here,
Yes.
you're saying draw it out like this?
Yeah. Right.
Or do I draw it out like that?
No.
So if I draw it out like this,
Right there. No. Too far.
oh, stop it?
Yeah. Stop.
An angle goes on forever. An angle is 2 rays.
Oh, so a centered angle. Oh.
A central angle also goes on forever. I just stopped the picture.
I'm saying. Oh.
So the central angle, if I drew the central angle again, this is a central angle. We just typically end the picture with where it intersects
I was thinking.
as a matter
Okay.
of it's
So
all-
the vertex for the other angle, the vertex has to be on the circle.
So for an inscribed angle, the vertex has to lie on a circle, and both its sides have to intersect the circle.
So that's the difference between a central angle.
Well, that's 2 definitions. Okay, so I think that laid out our definitions for what we need for a second here. We got that, we got that, we got that. And now we're ready to talk about RC constructions. And if we're talking about RC constructions, we're going to kind of put a pin in our geometry for a second. And we're going to go and we're going to now kind of do a little bit more of a deep dive into Euclidean geometry and get familiar with what these RC constructions are. But as a quick intuition for what they are, an RC construction is a construction you can make with a compass. I assume you've seen a tool like this before.
Yeah.
What does this tool do? It
Makes
gives
a
me,
perfect circle.
it makes so I can draw a circle. It helps me draw all the points the same distance from the point I mark off with my pin there.
It helps you find the radius.
So it enables me to draw circles, essentially is what it does. When the Greeks were using a compass, they would use a utensil hooked to a string. Pin the string where you want it, and then the utensil tied to the string and move it around.
Well,
The string is just the length of the radius.
Right, get the length that you want and move it around. So, logically equivalent. This can do something that the Greeks ones couldn't do. I can kind of lock in the angle and pick it up and move it. The Greeks couldn't do that. So we need to pretend that this doesn't have memory. I can't lock it in and keep it perfect when I pick it up and move it somewhere else.
Why not? Why couldn't
Greeks
you
could do that, they string.
You're assuming that you can perfectly hold it still over some distance.
Oh, string,
Whoa.
string type, right? Is that how they do it?
So, no, you draw the circle, okay.
Okay.
Now I want to draw a circle the same size over here.
Okay.
Yeah.
So now I gotta pick it up
Pick your
and move it.
Yeah, now you pull your string
Now you just
tight,
pull your
right?
string tight and do that circle.
Oh, I get what you're saying.
The Greeks didn't have a good way of keeping that information preserved. So, doesn't matter what the tools were.
Okay.
When we think of a compass, it does not have memory. It cannot preserve what its last measurement was.
Okay.
That's not built in. Second thing, typically you just have a protractor that comes with it to help you with everything. But when we're talking about RC constructions, R is in ruler, but a ruler without any measurement on the side. So again, no measurement, it's just something like this, a straight edge. Forget the curved part here. So it's just a straight edge and a compass. RC constructions. That's what you're allowed to use when you're doing an RC construction. And that's what you use in geometry. Okay, so that's what an RC construction is. Let's get our intuition now for why these things? Why is that what people use to do geometry? Why not different tools? Why are these the tools? And why is it valid to use these things? So, that's what we're going to dive into. With that, we're going to do a bit of a deep dive really quick into Euclid's way of doing geometry. So, going to Euclid, first he had his postulates. And he had 5 postulates. So postulate P1, I'm not sure the order here, but we'll reference them in whatever order I write them. We'll for sure write them. His first postulate is that if you have 2 points, then there is a line segment connecting those 2 points. His second postulate, P2, is that if you have a line segment, then you can extend it indefinitely as far as you want. So if you have a line segment, you can extend it into a full-blown line as far as you want. Third one was that if you have a point and a segment, a point and a distance, we're going to keep it a little bit simpler. Not quite exactly what he said, but close enough. If you have some segment, so if you have a point and some segment, then you have a circle. You can use that as your center, that as your distance, and you can mark out a circle.
That was P3.
That's P3. It's a third postulate. If I give you a segment, you can use that to construct a circle.
I don't remember.
Huh?
I just didn't remember that one.
This is for the Greeks, not for our geometry. We're putting a pin in our geometry, and we're going to do geometry the way Euclid did it. Euclid only had 5 postulates. We have something like, we have 20 something.
Oh.
So going and putting a pause in our geometry and doing Euclid's for a bit. Euclid's fourth postulate says that all right angles are congruent to each other. We had a similar one like that. Ours said that all straight angles are congruent to each other.
Well, we did the right angles.
We proved that this was the case. It was not one of our postulates. We proved all right angles were congruent to each other in our geometry.
So what's the difference between postulate and theorem or proof?
A postulate is one of the basic assumptions that you start with. A theorem is what you prove to be a logical implication of those assumptions.
So
Euclid has right angles are congruent as an assumption and proves straight angles are congruent. We had straight angles are congruent as an assumption and proved right angles are congruent. There's different starting points you can use to build up a logically equivalent geometry. His last one, P5, this is the only one we haven't introduced yet, but this is going to be the same as our fifth postulate. Again, not the same way he said it, but here it is. If you have a line, and you have a point not on the line, then there exists a unique line I can draw through the given point such that these 2 lines don't intersect.
Parallel.
Or in other words, they're parallel. It's called this parallel postulate.
Yes, okay.
Is there a way to write down 2 lines of parallel?
2 lines are parallel.
Yeah, just
We say
one.
L1 is parallel to L2 when we're saying that 2 lines are parallel. That's what we mean.
Yeah, that's exactly.
Okay. So those were his 5 postulates. And then we have what we called his common notions. He called them these.
Oh yeah. Is there a way to say, if I was writing up a proof, and is there a way to say angle A is congruent to the supplement of angle C? For word, the words, is there a simple way to say supplement and
No.
No?
No. Okay, and then he had what we call his 5 common notions. His first common notion was basically that identity is translative. He said things equal to the same thing are equal to each other, which means that if A is equal to B and B is equal to C, then A is equal to C. If things which are equal to the same thing, say it again. Things which are equal to the same thing are equal to each other.
Yeah.
That's his phrasing. Common notion 2 is equals added to equals or equals. So if A is equal to B, then A plus C is equal to B plus C. Equals subtracted from equals or equals. If A is equal to B, then A minus C is equal to B minus C. This fourth one, what is it? Things that coincide are equal. Coincide are equal. Thank you. This is where it belongs. I was looking for it. And then finally, the fifth one, C5, was the whole is greater than the part. Now, first off, what is Euclid doing here? Saying that these are postulates and these are common notions. What's the difference in his mind between a postulate and a common notion?
It's common.
Common notion.
It's like obvious.
Understood, right? Like it's.
No, you're thinking about it wrong. So let's go to our modern way of thinking about math and geometry. So in our modern way, we say, first off, there's this field out here called logic. It's as fundamental as it gets. It doesn't matter the field of study you're in, you're allowed to use logic. You can be coming up with an interpretation of a poem in a literature class. You could be doing history, you could be doing physics. Whatever it is, you're always and forever allowed to use logic.
Right.
So logic is common to every field of study. You build math on top of logic. So our geometry course was built on top of logic. Right?
Right. Wouldn't there?
Geometry is a very special field. It is not nearly as general as logic. It is not common to every field of study like logic is. And so these common notions are the things that are common to every field of study. These postulates are the postulates that we start geometry with.
So postulates.
So he's using this. Today we would call these, well, turns out he didn't quite put them right. Some of these should be up here. But we would call these three that he has listed out here theorems of logic.
Okay.
This has nothing to do, we also said these three are true in our geometry. We use these exact three things. We use these all the time. But these have nothing to do with geometry. These are consequences of logic. They're more fundamental than geometry. It doesn't matter what field of study you're in, you can use these facts.
Right.
These ones, on the other hand, are very specific to geometry. So that's the difference between his common notions and his postulates. His postulates are meant to be postulates in the same sense that we think of it. And his common notions, he meant to be almost as logical theorems, things that are consequences of Aristotle's Organon, the first book written on logic. So that's the separation there. But here's the 10 facts that he uses in all of his geometry. So now I'm going to start doing proofs in his geometry, proving his propositions.
Okay, first.
So,
Does
So
coincide.
this whole time we.
things which coincide. Here's a triangle. Now I'm going to draw another triangle. Notice how those two triangles perfectly coincide?
Yes.
Then they're equal.
Okay.
Basically, if I can pick something up and move it and they perfectly line up, then those two things must have been equal. It's kind of the notion he had in his head.
So this whole time we've been doing our geometry.
So this whole time we have been doing geometry using Hilbert's postulates. We weren't using Euclid's postulates. Euclid's postulates, notice that everything we have we can get in Euclid's postulates. But Euclid No, we can state everything Euclid has, but we can also state a lot more. For example, Euclid doesn't have any postulates about betweenness. He wasn't careful in thinking about betweenness. Often we use betweenness to talk about how this segment, how if here's a simple one. Draw a circle, two circles close to each other with a big radius.
What's the betweenness?
So they're close to each other. The point is, obviously those two circles intersect at a point.
Yes.
Right? You would have to make that argument. It would be kind of a tedious argument, but you'd have to make that argument using betweenness relations. Euclid never bothered making that argument because he never had the betweenness relations. He never bothered explicitly stating it.
Well, no.
There's a lot of things that you say obviously from the picture.
Yeah.
That's what Euclid did. We were very careful about it. Let's go back to one that you guys had to prove, or at least it was an extra credit for you. If you have a triangle and a line intersects one side and not the other side, then it has to intersect this side. Euclid would have just said that.
Right.
We had to carefully argue that using our betweenness relations and what exactly it meant to be on a side of a line.
Everything.
So we had to make things.
We were far more precise in what we were saying and far more careful about the assumptions we were making. Euclid relies very heavily on his pictures, which makes it a bit more fun to prove Euclid's way, because you don't have to be so precise. So I'm going to walk you through Euclid's way of proving things. We'll just do the first 5, then we'll do the RC constructions that the author specifically has here, then we'll move to chapter 8. Okay, so his first one, and I'm going to read the language to you so that you can get a feel for how weird this kind of sounds.
Real quick, did you decide to do all chapter 8 today as well?
I don't know. All right, so proposition 1. He's proving these propositions are true.
Okay.
Okay, proposition 1. To construct an equilateral triangle on a given finite straight line. Okay, sounds kind of funny. What's he saying? He's saying if I give you a finite straight line, our language for that is a line segment, AB, then you can construct an equilateral triangle
That's true.
with that. Right?
Yes.
Yeah.
Okay, so let's go over the proof now for this, thinking about the way Euclid does. So first I have a segment and a point which gives me a circle. So one would be, construct circle A with radius AB. So I'll construct a circle right here. How do I know I can do that?
Because it's
Because
three
it's
postulates.
This is using postulate 3. Postulate 3 says I can do that. So I do that. And I construct I'm not going to draw out the whole circle, but only part of the circle. But there's a whole circle around. If you draw all the circles every time, your picture becomes a mess really quick. Number 2, I can do the same thing, but circle B, using proposition 3. So I can come here and I can construct a circle. Right?
Yes.
3, let C be one of the points where the circles, where the circles intersect.
You're trying to make an equilateral triangle?
Yes. So we have C is one of the points where the circles intersect. Notice the circles intersect at the bottom and at the top. Right? If I were to have drawn out the whole circle, this circle also has a bottom half down here. This circle also has a bottom half down here. And so there's a second point of intersection.
Yeah.
So call one of the points that they intersect C. Doesn't matter which one. Right? Now notice Euclid does not argue that those circles have an intersection point.
It's obvious.
He thinks it's obvious from the picture. So we would have been far more careful. He's just throwing it out there. Look at the point where they intersect, because obviously they do. So it's a bit more fast and loose. So now we have these segments. So 4. Then AC is congruent to, he was said equal to, but we'll say congruent to, AB. AC is congruent to AB. I know this is congruent to this. Since C and B lie on circle A. I name a circle based off of its center point. Sorry. As a general rule, that's what I do. So this circle centered at A, I'm calling circle A, and this circle centered at B, I'm calling circle B. Okay, so notice that C and B are points on this circle.
Right.
And so they're equidistant from the center. They're both radiuses of the circle. This segment is a radius of this circle, and this segment is a radius of this circle. You see that?
Yeah.
Okay. 5. Then CB is congruent to AB. CB is congruent to AB. Then CB is congruent to AB. Same thing. They're both points on circle B. I guess it doesn't really follow as well. Since A and C lie on circle B. This is a radius of circle B. This is a radius of circle B.
Yes. Okay.
So those are congruent. And then so finally, we have CB is congruent to AC. Then CB is congruent to AC.
Because of common notion C2.
Because of common notion, C1. Things equal to the same thing are equal to each other. So this is by C1. And so we got an equilateral triangle. All the sides are equal to each other.
Oh.
Right?
Yeah.
Okay, let's do a second proof.
Now,
Which means the angles would be equal to each other, right?
Yes, that happens to be the case, but we haven't proven that yet. Next, proposition 2. To place a straight line equal to a given straight line with one end at a given point. So what does that mean? It means I've got some segment here, AB. Not sure how I'm going to draw lines up. I've got some segment here at AB, and I've got some other point here, C. My job is to construct from the point C a segment the same length as this segment.
You're in the circle again.
I'm going to do the circle again.
Are you proving all
Say
the
that again.
postulates?
No, you do not prove these. You use these to prove, you use these to prove. I reference these.
Okay, say
Well,
one more
what are
time.
you trying
Okay.
to prove?
What are we trying to prove?
One more time.
Trying to prove. So I give you this line segment,
Okay.
and I give you this point.
Okay.
I tell you, I want you to go and construct the line segment this long at that point. So you can't say, okay, pick it up, measure it, and go over and do that. Right? This is why your protractor, or not your protractor, your compass doesn't have memory. You can't say, okay, be really careful, measure that up, and then come over here and then draw a point the same distance away.
So the rollers didn't have measurements.
Well, you're getting focused on the limitations, and maybe there's these physical ways we could come up with doing it. Look, if there's a way, this is basically preserving the memory. If I can do this proof without it, I'm showing you that you don't need to preserve memory. And so you don't need to rely on this careful, did we hold the string in the right place as we moved type thing.
Because you can prove it.
Because you can reset the measurement every time. You can pretend it doesn't even have measurement. And so if you were laying out, some big construction plan, think about how carefully you need to measure out some things. I gotta build a circle over here and a circle over here of the exact same radius. And so you're trying to lay that out. Anyways, so that's what we're trying to do. Create a line segment from C the exact same long as that. We don't know which direction, we just need to create one.
Okay, so there's a circle.
A circle what?
There's a circle from A.
No, you don't even need to do that.
Why not?
Okay, there's a circle centered at A, so you're saying that there's that circle.
Yeah.
Okay, so you're thinking we have this circle.
You can't freaking push your pen. Yeah, you should do it.
Wouldn't you say,
So always and forever, well, not always and forever, as a general rule, you typically need to use a previous proof to do the next one. That's fairly standard.
That is the standard.
So first thing I'm going to do is I'm going to construct an equilateral triangle using C and B. So I construct some equilateral triangle, we'll call this other point D. But I know that's congruent to that's congruent to that. So I'm not going to bother writing out all the words here, but each step I take, I'm just going to write how I'm justifying it. So this was justified by, we'll call it, we're used to calling them theorems. This is justified by theorem 1, the first thing we proved. You can construct a triangle. So I'm going to say, maybe I'll say triangle BCD, triangle BCD, and we're justifying that by theorem 1. So we know that we could have constructed that triangle. We already have those steps in place, so just go follow those steps. They're already there. And so a lot of his proofs are actually laying out steps for constructions. Here's how you would do this thing. Here's how you would do this
It's
thing.
much more relaxed.
It's much more construction based.
Yeah, it's not as like.
Okay, so now we got this equilateral triangle, right? Now remember, we're trying to, from the blue point, construct a segment the same big as this segment. Let's mark our starting data so that we don't lose track of it. Okay. So now what am I going to do? I'm going to come centered at B. I'm going to create the circle with radius AB. So 2, I'm going to do circle B, and this is, we can justify that with postulate 3. And so we got this circle. Now I'm going to extend this line until it hits that circle.
from B or from D?
This segment. I'm going to extend this segment until it hits that circle.
Why not? Yeah.
Now the way that,
You don't want to extend it right there though. You want to extend it from BC forward.
oh, we're good so far. So I want to find this point right here is so far as E, right?
Okay.
So 3, now maybe you mark the radius here. Circle B with, what was our radius? AB. AB is our radius. Now we're going to do circle D with radius DE. So this was, oh, sorry, we got to extend the line. So first we did the circle, that was proposition 3. Then I extended segment BD. So 3, I constructed a line through BD, extending it. We could justify that by proposition 2. Postulate 2, thank you. And then our next scene would be, now I'm going to construct my circle. So now I do circle D with radius DE. So that's our radius. Again, that's proposition 3. Now,
Why? How's that useful at all? We're not trying to figure out a thing that's length to DE. We're trying to figure out what's
so
length
I
to
just
AB.
constructed a circle centered at D with this as its radius, right? So I'm going to draw that out now.
Oh, now you're gonna do another circle and then from.
No, we're done with our circles. You'll see.
I know you're not another circle. You're gonna continue
This-
circle DE all the way around.
Right. So
And then-
DE,
so
trying to draw it
C-
somewhat decently. Here's
CE
DE.
prime, whatever you want to call it, point is congruent to.
So this is the circle centered at D with radius DE, arced out here.
So this, were we specifically trying to prove that the point starts at C?
Now,
And then the line starts at C?
extend DC.
Just wait a second.
We extend this out,
Right, and thus
and then call the point where it intersects here.
E prime.
and then we can call this point, what do we call it? F.
So CF is congruent to AB. But
So,
where did it say it? I wasn't reading the thing, but did it actually say that the starting point needs to be C and then another point? Segment is C something? Or
So,
could it have been
where's-
something where C is between those 2 points?
now, so we started out with a segment and a point. Our job was to construct a segment congruent to this one
Uh-huh.
that has one of its endpoints C.
Okay, and I was
Okay.
wondering if C could have been in between. Because if it could have been, you could have just started the circle B and be done. So then it could have been BF with C in the middle.
So if I started my circle at B, what radius would I use?
BA.
So then, oh, I see what you mean. Okay, yeah, that would have been easy. In practice, what this is telling me is I can treat my compass like it has memory. That's in theory what it's saying. I've got my compass here. I'm saying I can come pick it up and recenter it at this location, and this tells me how.
Oh.
So now notice that this has the same length as this. How do I know that?
Oh, EB does, yes, okay. Yeah.
This has EB, has the same length as AB. I know that because they're both radii of the circle B.
Right.
And I know that ED is congruent to FD because they're radii of the same circle. And so then I know EF is congruent to FC. This is congruent to this. Since this whole thing is congruent to this whole thing, this piece is congruent to this piece. How do I justify that?
Because BD.
Equals subtracted from equals are equal. So that's using combination 3.
So what
Right?
Kendrick was saying was, if you created a full circle with the radius B to A,
Kendrick was saying, here's AB, here's some point C. He's saying, okay, just construct this circle centered at B with radius AB,
Right, I didn't understand that C.
and then draw the line that goes through C. This has the same length as this, and it goes through C.
Yeah, that's why I said scroll.
But that's not our job. Our job was to find a segment that starts at C and goes out. Not one that intersects C, but that actually starts at C. In other words, I want to take my compass, I want to pick it up, and I want to set it down at C without losing how far out I had it. That's what it enables me to do.
Okay, let's say at where the point BC, where the line BC intersects the circle, let's say that's F.
Okay.
Okay, let's say the line goes on forever.
Yeah.
Let's say let's say there's a point on that line that is the same length as BC.
There is.
Okay. So
But how do we find it?
Let there be a point on line B. Would it be BF?
So you're thinking now in terms of our postulates. From our postulates, we know that there is a point C prime that satisfies this property. Euclid is interested in constructions. So notice that his postulates are all very construction based. You don't get to just say that that exists in Euclid's geometry. For Euclid, you've got to construct that point to show it exists. Constructing and showing things exist are one and the same for Euclid.
Okay.
And so you have to come up with the construction that gives you that point. Now it turns out there is that point. We just found it.
Euclid says, just look at the picture.
Here's the construction that shows it. So notice all his postulates, these are all very construction based.
Very.
This says 2 points can be connected with the line segment. That's what your straight edge gives you. If I have 2 points and I hold up my straight edge to those points and I decide I may connect them, that's logically equivalent to I just used postulate 1.
Right.
I take my straight edge, I'm like, I should have made that longer. Let me extend that. Okay, that's better. Okay, I just used postulate 2.
Now you just straight edge. Say, look, there's a circle.
Or I can take my compass. I could have said, oops, I want to construct a circle here. It's going to look bad because... But then I can use my compass to construct a circle there if I want to. Oh, I just use this.
Okay.
So every time you do something in the picture, you're using a postulate directly.
So are you?
Or a theorem, but the theorem reduces back to the postulates.
Right.
So every pictured thing you create is logically equivalent to showing it's a logical implication of these things.
Right.
Constructing something and showing it's a logical implication of the postulates are the exact same thing in his geometry. That's what's so fun about it.
So he kind of depended on pictures.
Very heavily depends on these constructions, these pictures, yes.
Yeah.
But we proved that pictures lie.
Yeah, we talked about how pictures lie and how Euclid's being a bit fast and loose. Now it turns out he never screwed up. He never accidentally let a picture trick him into thinking something was true that actually wasn't true. So Euclid was really careful.
With everything he did, he was never wrong.
With everything he did, he was never wrong.
So,
But we can
we
prove
where did
more.
where they find this?
We can prove more than he could prove, and we prove more precisely. So we'll talk about some things that Euclid could never prove that are true in the geometry. And it was just impossible for him to prove it with his postulates.
With only a Ruer in the compass.
Yeah.
So, where did they find his teachings? In the music, in a library or something?
Where did they find his teachings?
Yeah, I'm saying he's ancient of days, right?
Euclid, yeah. So he wrote a
Yes.
series of books called the Theorems.
And they were in a library somewhere.
Oh, yeah.
And it's one
But-
like they found it written on a rock or something.
No, nothing like that. The Greeks wrote tons of things. You've heard of the Great Library of Alexandria.
Yeah.
That's
In Egypt.
not long after the, well, it's Egypt, but it's the Ptolemies.
Yeah.
That's not long after the golden age of Greece occurring. That's a little bit after. You have the golden age of Greece, then you have Alexander.
Great.
Well, I guess you have Philip, then Alexander the Great, and then
Yeah, Ptolemies.
the Ptolemies. The first Ptolemy was a general of Alexander the Great.
He was half brother.
And so Ptolemy was a student of Aristotle.
Right.
So that's how closely related these guys are. How close they are to each other in terms of years.
Was Euclid, what time period was he?
Euclid is a bit after.
So he wasn't, what do you call him? He wasn't the same time period as Aristotle.
No. By the time we get to him, we are well into the Hellenistic period.
Yeah, about Aristotle.
Yeah.
So I'm not sure how many years are between them, but I would guess it's 100 plus.
Is Euclid a pretty famous guy? Like, would he be in a world history book?
Yes, you've definitely heard the name Euclid many times. He's the father of geometry. That's how he's referred to, father of geometry. Geometry was the first rigorous body of knowledge ever developed. It's what the Greeks dedicated themselves to. Anyways, so there we go. We constructed a segment congruent to our given segment from that point. It doesn't look very congruent, but pictures lie. Unfortunately, I don't have a good compass I can use for a whiteboard, and we can make these pictures all pretty. But if you were to redo the construction on your paper with just a compass and a straight edge, you can make it look all pretty and see how obviously true it is.
There used to be one in the other room that kind of distracts. It was chalk.
Yeah.
Should we get you one for this room?
Alright, so let's move on to his third proof. His third proof, if I remember right, is basically our side angle side one. Oh no, his third proof is super simple.
Are you just online?
Yeah, I just pulled up a list of his propositions I'm just reading.
So, they're not in this book.
No. But I mean, Euclid is in the public domain. You were talking about Euclid's Elements. It's the second most published book in history.
Bible being first.
The Bible being the first.
So,
And there's good evidence to suggest that it was the second book printed after the Bible. So Gutenberg with the printing press, they did the Bible. Next came Euclid's Elements.
who wrote this book then?
This book is just Charles Darwin.
Who, you're saying the one that we're reading from?
Yeah.
Some people over in England. It's 3 mathematicians over in England put this together as a high school geometry textbook. They are using the axioms of Hilbert.
There's a huge
Hilbert was the giant he was the Einstein of mathematics in the year 1900.
There's a huge
So the teachings in this are Hilbert's, not Euclid's.
So the postulates there, we are using Hilbert's postulates. We are not using Euclid's postulates.
It has a review of chapter 6 printed 3 times. So funny.
But to get those ones in Masada, they had to specially call the publishing company and order some.
You're on the right voice class, right?
No, but they are the same book that he uses.
Why did Masada have it?
They had Aaron teach once, and he said he wouldn't do it unless they got these books.
Aaron,
Timpson, my cousin, Don's.
are you present?
Oh, it was,
Yeah.
he taught it there, or?
I think it's Masada. It must be Masada because they're in Masada's library.
And you books are freaking out too.
Anyways, postulate number 3. To cut off from the greater of two given unequal straight lines, a straight line equal to the less. So what's he saying there? He's saying that if you have two unequal line segments, so one's less than the other, then you can cut off a portion of this segment equal to this segment.
Oh, yeah.
Now this is real easy. From our previous theorem, we know that I can come to this point and construct a segment congruent to this one. So I know that I can come over here and make segment A, B, C, D, A, E, so that this is congruent to this. That's using the previous theorem.
Okay.
Now, create our circle, and wherever that intersects at, call that F, and now that is congruent to that because they both lie on the radius, and so it's congruent to that because equal to the same thing or equal to each other. Things equal to the same thing or equal to each other. So there we go. We just made a segment here congruent to that segment. That's all that one was. So that was a pretty simple one.
If you made two circle, that's where they.
All right, reset.
Oh,
No, that makes
I
sense.
think I got you. Yeah.
Oh, okay. All right, his next one now I think is the side angle side one. And this is the weirdest of them. Here's what he says. He says, we have two triangles, A, B, C, and D, E, F. Sorry, I didn't draw it too good. But I was trying to draw it. We know that this is congruent to this, we know that this is congruent to this, and we know that this is congruent to this. He says then they're congruent to each other. How does he prove that they're congruent to each other? You're going to see he does this in a much less satisfying way than the way we did it. He says, take this point B, basically we're thinking of picking up this triangle.
Yeah.
I'm going to take this triangle, I'm going to scoot it over, and make sure D lands exactly on A. So D and A are the same point.
Okay, okay.
How do you do that though?
Hey, yeah.
You can't move a
Yes.
string.
How do you, when you are making a proof, how would you say that? Because in our homework, there was.
This is not how we would say it. I'm giving you Euclid.
Well, okay.
We're never gonna do this wrong.
Well, we did in 6. It was.
So we're taking this line,
It might have been the same.
and we are placing it there.
It wasn't 2 separate.
AD.
So he's just gonna move it over somehow.
Well, he's not actually moving it over. He's saying, imagine if he did. I'm going to show you why these triangles have to be the same. So this isn't going to be a construction. This is stating a property. Okay. So he says, if you were to put that on there, if you were to take that point out of the triangle and put it there,
Oh,
then since AB is congruent to DE, and things which are equal coincide, then these two segments have to coincide with each other if I line them up. If I line them up, then these two have to coincide.
That's so unsatisfying.
It is very unsatisfying. And then, since this angle is congruent to this angle, and remember the angle is the whole shape, and since which things that are equal coincide, then this side of this angle has to lie on this side. So when I line it up, that angle comes right here. And how far does it go? Well, since this side is the same length as this side, then F would land directly on C. And so he's using things that coincide or equal, very similar to how we use our side angle side postulate. They kind of do the same thing. Anyways, and so that's how we get, okay, so those three triangles are congruent to each other because they're the same triangle. So using this thing a lot.
Yes.
Yeah, not very satisfying, but that's it. All right, next one. Here's one that you'll find very satisfying. Because let's see, isosceles triangles one. Oh, but he goes a bit further. So he says not only are the base angles of an isosceles triangle congruent, but the angles under the base angles are congruent. Okay, so this will be a more fun one. So we've got some triangle here, some isosceles triangle, A, B, C. I know this side is congruent to this side, right?
Yeah.
And I know that this angle is congruent to itself. So I know triangle ABC is congruent to triangle CBA, which gives me that this angle is congruent to this angle. That's how we prove the base angles were congruent. Because triangle ABC is congruent to triangle CBA. You're thinking about two triangles
Yes.
laid over each other in the same picture.
So,
This triangle is congruent to flip it over that triangle. That's what we proved.
oh,
Well, this is what we already did. That's a perfectly good way to do it. We're saying triangle, you can draw it out as two separate pictures if you want, but we're saying triangle ABC is congruent to triangle CBA.
Yeah, I remember doing that. It was kind of cheesy.
No, that's a great way to do it. It's the best way to do it. Look and see two triangles in one. The segment C to B is the same as the segment A to B. C to B is the same as A to B. That's what this says.
Okay.
And the angle ABC is the same as the angle CBA. CBA, ABC, yep. And BC is the same as BA. BC is the same as BA, yep. Therefore, those two triangles are congruent.
you're saying A to C is the same as A to B? And C
Yes,
to B?
so now I know that angle A is congruent to angle C. I know angle B is congruent to angle B. And I know angle A is congruent to
Angle.
angle C. And same with the side lengths, listing them out.
How does that make it that A to C, side length A to C is the same length as A to B?
It doesn't.
Oh,
So
I
let's
thought-
list out the signless relations that this are saying the same.
I thought you said-
This is saying AB is the same as CB. So it's saying AB is congruent to CB. It's saying BC is congruent to BA. And it's saying AC is congruent to CA. So what did we say AC is congruent to? We said it's congruent to CA. What did we say AB is congruent to? We said it was congruent to BC. What did we say CB is congruent to? AB.
I thought you said CA.
So it's two triangles laying in on each other that are congruent to each other. Okay, that's how you get those ones. Those angles are congruent. Showing these angles down here are congruent is a harder story. So what do we do first? Well, first we extended the lines of the triangle. Okay, that's using postulate 2. Perfectly valid thing to do. Right? So kind of erase these now, and we're going to focus on the bottom one. I don't know if it'll matter in our picture, but try and keep it as clean as we can. Now I'm going to pick any point down here, A, B, C, any point down here, D. Nothing special about it. Just pick the point. Now I'm going to come over here, and I'm going to mark off a segment here so that it's congruent to this. How do I know I can do that? Previous theorem. I had this whole line. I can mark off from the line a portion congruent to a smaller segment.
Yeah.
That's the previous theorem. Okay?
So you're saying find on the other side a point on the line that is congruent to AD.
Right. So now we know we can do that. That was the previous theorem. The previous theorem was if I give you a segment and then something for sure longer than that segment and a point, I can go from that point and get a segment the same big as that. That was the previous theorem, which very similar to our existence postulate for congruent segments. Anyways, okay, now we got that. Sorry, my picture is lying a lot. Let me try and keep my E and my D roughly the same level. A little better. Okay, now I'm going to connect those 2 points and connect those 2 points. Or in other words, I just use this twice. Okay, now notice the 2 triangles we have here. If I draw them both in blue, that draws everything in blue. So let's look at this triangle right here. the triangle with the 3 blue points. You see that one?
Yeah.
And now look at the same triangle, except for using DCB. That same triangle right there.
Okay.
So those are the 2 triangles we're talking about. Notice that EB is congruent to DB. So I have EB is congruent to DB. I have angle B is congruent to angle B. And I have BC, or BA, is congruent to BC. So I just barely showed triangle EBA is congruent to triangle DBC by our previous theorem, which was a side angle side theorem. Triangle EBA, the one with blue points, is congruent to triangle DBC. That triangle is congruent to that triangle.
Okay.
You see it?
Yeah.
Okay. So, what does that give me? Since they're congruent, then this angle I'm about to mark in blue, these angles are congruent. Right?
Yeah.
And the bases of each of these triangles, this line and this line, are congruent. So this line is congruent to this line. Taking the whole line segment. You see that?
The side angle side.
Since the 2 triangles are congruent, now all their sides must be congruent and all their angles must be congruent. Okay? Now, notice what we have. Triangle AEC, this triangle, is now going to be congruent to this triangle by side angle side.
Right.
Because they both have a side the same, an angle the same, and a side the same. And so the triangles are congruent, which means that this angle in each of the triangles, so in this triangle, this angle is congruent to in this triangle, this angle. And so the angles at the bottom are also congruent. So I showed that this angle was congruent to this angle first, that was congruent to that, and then I showed this is congruent to this.
Question. What does he say about supplementary angles? Nothing?
It's just a definition, supplementary.
Does he say anything about
Their angle sum is a straight angle. So Euclid's definition of a supplementary angle is the same as ours.
So, but his you can't just say congruent. How do you put this? Congruent angles, their supplements are congruent.
If angles are congruent, then their supplements are congruent.
Yes.
We proved that. We proved that not that different from the way Euclid would prove it. But
He hasn't proved it yet, so we can't.
we haven't done that proof yet. Okay. But yes, if we already had that, then this would have been much easier. Okay, so that gives you a taste for Euclid's proofs and how construction-based they are. Now, limitations on this. So there were 3 problems that stumped the ancient Greeks. Problem number 1 was the problem of trisecting an angle. We'll do an angle bisection here in a second, just trying to follow the order that the author does it now. So now we're going back to the book. Did a quick detour with Euclid. So going back to the book now. The ancient Greeks, there were 3 problems that stumped them. Problem number 1 is trisecting an angle. How do you trisect an angle? How do you break it up into 3 equal parts? So that was one problem that they got stuck on. The second problem they got stuck on was the duplication of the cube. Okay. So the duplication
How
of
do you trisect an angle?
split an angle into 3 equal parts. If I give you an angle, I want you to trisect it. Divide it up into 3 pieces.
Isn't that pretty simple?
You get a ruler and compass to do it.
Well, to trisect an angle,
Yes.
you could use a circle.
Let's do the construction really quick for bisecting an angle. So bisecting is really easy. Trisecting is a whole new beast. So let's do bisecting really quick.
Well, wouldn't you just create a circle, find 2 points on that circle?
Create the circle centered here.
Yes, centered at point O. Or,
Okay,
yeah.
so we've got our circle.
Find 2 points on that circle
That intersect these. Does it randomize 2 points?
between ray A and ray B.
You're saying 2 points like that?
Now between them, or how would I say on the interior?
So pick 2 points in the middle. Okay, there and there.
Connect them to point O.
Connect these to point O.
Didn't you just?
No, I split it into 3 pieces. I did not split it into 3 equal pieces.
What is? Oh, equal. That's
Equal
what
pieces.
trisecting it.
Yes. Trisecting is breaking into 3 equal pieces. So I'll show you how to bisect an angle really quick. That's one of the constructions the author does. And then you'll see how trisecting might not be as easy as it first seems. So here's, how do I trisect this angle? Remember, I only get a ruler and a compass.
Just we bisect.
Yeah, bisect, sorry. Don't let me say it wrong. How can we do that? Well, with my compass, I can draw a circle, da 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 da, and find 2 points here and here that are equidistant from O. So we'll call it A and B, and what do I know about A and B? They're equidistant from O. Right?
Right.
And now, I can come here, and I can draw a circle again, centered at A. We can use the same radius here. Draw that, and we're going to swing around. Drawing that circle around A, we're going to have an arc point over here. So the edge of the circle might look something like this. I don't know.
So how do you know your radius?
Same radius. I put my compass here, here's my radius, and now I'm drawing a circle centered at A.
Oh.
And so it's going to fling over here somewhere. And I do the same thing at B, and it's going to fling over here somewhere. And where those intersect, create this shape. And I know that this is also equal to that. Because they're all the same radius.
Let's do a line from O to C.
Now we do a line from O to C. Good letter. A line from O to C.
Would all 4 of those lines be?
Now notice that by side, 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 this triangle is congruent to this triangle. This side is congruent to itself. That side is the same as that side. That side is the same as that side. So by side, 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 these triangles are congruent. Which means that this angle is congruent to this angle. And so I bisected it. I split it into 2 equal parts. So that's bisecting an angle. Trisecting an angle
Flipping hard.
turns out it's a little bit harder. And so that's one problem that stumped the ancient Greeks is how do you trisect an angle? So if I got an angle, how is it that I can divide it up into 2 separate pieces? Problem number 2, doubling the cube or something like that.
So they figured out how to bisect.
Yeah, that's real easy. Euclid was a much smarter man than I am.
You could even just, you could bisect it again.
You can bisect each of those sides again.
Yes.
And so dividing it into 4s, that's trivial. Dividing it into any multiple of 2, that's trivial.
Well, no, you could say COA is connected to COB. It's a different angle. Now just bisect that and then bisect COB.
Right, I can easily bisect this now.
Yeah.
And I can easily bisect that.
3 equal parts.
So now it's 4 equal parts.
Oh, shit, yeah.
And then I can easily make it 8 equal parts, and 16 equal parts, and 32 equal parts. Splitting it in half, splitting it in half, splitting it in half. So, yes, that's trivial from there on out. Trisecting it, that's a different beast. What was the other problem that they had? Given a cube, find the length I need so that the new cube I construct with my new length gives me a cube of double the volume. So if this is 1 unit in its length, what does the length over here need to be? What does x need to be? I want to construct that length so that the volume is double. Now, if the cube has length 1 here, what's the volume of this cube?
2.
1 times 1 times 1.
Yeah.
1 cubed, which is 1.
Huge.
Length times width times height. All right, over here, what would my length, width, and height have to be if my volume is going to be 2?
Very complicated.
Well, it just has to be the cubed root of 2. You come across that before?
Yes.
Square root and cubed root. Quick example. The cubed root of 8 is equal to 2. Because 2 times 2 times 2 is 8.
Yeah.
So the cubed root of 2, well, that's some irrational number. But that's all they're talking about is the cubed root of 2. So essentially they were wondering, how can I construct a segment that has length cubed root of 2? Notice square root of 2, that's real easy. If I've got a square, and I say that that's length 1, then just write its diagonal. Now that has length square root of 2. Now, if you have length 1, can you come up with something that's the cubed root of 2? Using a compass and ruler. Come up with some construction. If I've got, you give me a 1 meter segment, my job now is to construct a segment that is cubed root of 2 meters.
Wait, why do you find the cubed root? Cubed root of 2. Why not?
What is a cubed root of 2 times the cubed root of 2 times the cubed root of 2?
2.
4.
What is this times this times this?
2.
It's equal to 2.
Oh, yeah.
Because it's a cubed root of 2. The same way that the cubed root of 8 times the cubed root of 8 times the cubed root of 8 is 8. It's the cubed root. It's the one that you have to multiply by itself 3 times to get back to where you started. Right? Okay. So that's what they're trying to construct. Something that has that length. Square root of 2, easy. Cubed root of 2, that's what they were stumped on. And you can see how this might be used in a very practical problem. I've got a box this big. I need to double the volume. I've got some square container. I need to double the size of it to hold more water. What should my dimensions be? And so I need to calculate that out with some construction.
With a cube that has the volume of 1, this is 1, that's 1, that's 1, that's 1. Every side
dimension.
length on it is 1.
Correct.
Correct? So to double it,
Then you
every
need
side
cubed root of 2
length
by cubed root of 2 by cubed root of 2. So like your length times your width times your height gives you exactly 2.
In order to double the volume.
so
The volume is length times width times height.
on the double volume, every side length wouldn't be 2, it'd be a point where.
It wouldn't be 2. If I created a box that was 2 meters wide, 2 meters tall, and 2 meters deep, it holds 8 cubic meters of water.
Right.
Oh.
Its volume is 2 times 2 times 2.
Which is 8.
Oh. So you need to find what?
I want the volume of this to just be 2.
Which is the cube root of 2.
So its length needs to be the cubed root of 2, its width needs to be the cubed root of 2, and its height needs to be the cubed root of 2. So its total volume comes out to 2. So it has exactly double the volume of that thing. And then the third problem, it's probably the most famous of them. They call it circling the square, or squaring the circle. Squaring the circle. So I give you a circle. Your job now is to construct a square that has the exact same area as the given circle.
Oh, that's tricky.
So you can't do something stupid like, okay, let's just find the square that inscribes the circle. That's real easy. No, those have very different areas.
Very.
We gotta learn how to find the area of a circle first, right?
Well, they knew how to find the area of the circle. They knew the formula, pi r squared.
Times pi squared.
Oh yeah. Can I ask something?
Go
Why
ahead.
did they get pi? Like,
Pi by definition, so we haven't gone to it yet, we'll get to it. Pi by definition is the circumference of a circle divided by its diameter. That's its definition. If I ask you what pi is, you say it's 3.14159, and then I yell at you and I throw a book at you. And I say, no! This is what pi is! It's circumference over diameter. 3.14159 is some cute numerical approximation, blah, blah, blah. Who cares? This is its definition. This is what pi is.
yes.
It's circumference over a diameter. It's that ratio. What are these numbers? Who cares? What exactly is the number? Who cares? How do you write out the decimal expansion of it? Who cares? Here's its definition. This is what it is. So you're used to thinking about it as some numeric approximation. No, its definition, circumference over diameter.
Does that mean pi changes?
No, that's what's amazing.
Why? How-
Is the circumference over the diameter is always the same number.
What's the circumference?
Circumference is the distance around a circle.
So how do you
The
find
distance around it divided by its diameter.
Is it-
Well, we haven't gotten to this yet.
Okay, just get off. Say, yeah, we haven't gotten, but how do you find circumference?
How do you find circumference?
What is the
360 degrees.
I don't know. You mean like if I...
what's the formula to find circumference?
So you're used to thinking about this very algebraically where someone gives you numbers. And you have to use your numeric approximations, get some numeric approximation for some number. Okay, so what I think you're looking for is that circumference is 2 pi r. That's what I think you're looking for. Because diameter is the same thing as double your radius. And now, it comes instantly from the definition.
But that means that you use something to define itself.
Yeah, you don't use this. This is not a definition for circumference. This is how we can calculate a numeric approximation for circumference if we know the radius, and since we already have a really good approximation for pi.
Interesting.
So this is a calculation you do to get an estimated number for some distance.
Oh, the circumference of a circle can change, correct?
Yeah, big circles have big circumference, little circles have little circumference. But the ratio, the diameter to the circumference. If I take any circle and I take its diameter and I think about its diameter now as a string. So this is a string, right?
Right.
And I wrap it around. My first diameter gets about this far. My second diameter gets about this far. My third diameter gets about this far. And how many diameters would it take me to get all the way around the circle? It would take me 3.14159 diameters to get exactly around the circle. No matter the size of my circle. Bigger circles have bigger diameters. Smaller circles have smaller diameters. But the ratio of the circumference to the diameter is always the same. And it's pi. It's constant. And that's what pi is. Ratio of circumference to diameter. 3.14159, that's some numeric approximation for the value. That is useful when we're doing these types of formulas, but it's not the definition. But that's where you start trig. Start trig with the thorough definition of pi, and then of a radian, and then of sine and cosine. With those 4 definitions, you're ready to go.
You know how you said like trig is a bunch of memorizing and stuff?
It's the way it's typically taught. You're given a sheet of what we call trig identities and trig formulas that students just try and brute force memorize.
The kids in trig said that John Colley said that geometry is a bunch of memorizing too.
No, far from it. The whole point of geometry is to see how your basic assumptions entail all the theorems. That's also supposed to be the point of trig. That's also supposed to be the point of algebra, and of topology, and of number theory, and of pick your field of math. It's all the same thinking. It's just not the way it's hardly ever taught.
Because it's hard to say that.
And so instead, you're given a bunch of things to memorize over and over again. And so when you took geometry back at Masada, they said probably memorize these theorems. Here's some example using the theorems, where we give you some numbers. Let's see if you can solve for the numbers. And that's all it was over and over again.
Kind of was. When we did geometry though, there was very, very few classes and stuff. We wrote them all down, but there wasn't
Right.
It wasn't as many as we did.
They might have taken the time to say, oh, by the way, these theorem things are somehow entailed by these. Would you like to see that? Too bad. Because it's hard to show it, and it's hard to walk you through all the steps. Anyways, so these were the 3 problems that the Greeks got stuck on. Using these constructions. Now it turns out, all 3 of these problems are impossible to prove using just Euclid's postulates. That's what we mean by Euclid's geometry is still somewhat limited. Everything Euclid proved, we also prove. But we can go beyond Euclid.
We can prove those.
Since he wasn't precise enough, he kind of limited himself. And so there's things that are true that Euclid's geometry just couldn't handle.
Right.
And so the Greeks, they spent forever trying to figure out the answers to each of these problems and just couldn't. Now we know, provably, you cannot do any of these constructions from these postulates. Kind of fascinating. So, It's amazing what they did, but they had some problems that they thought of as really hard problems, and it turns out not only were they really hard, they were impossible. Alright. Two more constructions that the author does before we move on to checkering. So he does a construction. Given a line segment, AB, our job is to construct a perpendicular bisector. So we want to construct a line that goes through the midpoint of this segment at a 90-degree angle using our RC constructions. With me?
Yes.
Okay, so how do we construct that? So first thing we do, I'm going to come to A, and I'm going to draw this circle, and then come to B and draw its circle.
Okay.
So if I come to A and draw its circle, something like that, come to B, draw its circle. Obviously this is very imprecise. Those two circles intersect at 2 points. Now the fact that those two circles intersect at 2 points, the author has as theorem 7-something. He says, basically it's absurdly complex to prove that those two things intersect somewhere. So we have it as a theorem that we don't prove, and we're just going to accept it as true. That if your circles are close enough to each other, so that the distance between them, if the distance between your two circles, if both your circles have the same radius, and the distance between them is less than the diameter, then the two circles are going to intersect at 2 points.
Right.
That's what we're going to assume. It's not that it can't be proved in our geometry, it's a pain to prove it, and the payoff for going through the heavy proof isn't worth it. Okay, so anyways, they intersect at 2 points, C and point D. And now we construct the line through C and D. Okay, pictures lie, but you get the idea so far, right?
Yes.
So now, let's look at some triangles. Drawing that triangle, drawing that triangle, drawing that triangle, drawing that triangle. Okay, what do I know? I know that this side is the same long as this side, because we're both radii of that circle centered at B. And I know that this side is the same big as this side, since they're both radii of the circle centered at A. And since my circles have the same radius, all four of those sides are actually equal to each other. So I have that side is congruent to that side is congruent to that side is congruent to that side. Because they're all radiuses of these two circles, which have the same radius. With me so far?
Yeah.
Okay. So let's see, what do we know? We know that, let's see, I want this is congruent to this. So I know that this triangle, CAD, is congruent to triangle CBD by side, side, side. So we have this diamond shape. Cut the diamond down the half in the middle, and that has me a triangle on either side. The triangle on the left is congruent to the triangle on the right by side, side, side. This side's the same as this side the same as this side, and their shared side's the same as their shared side.
Right.
So those two triangles are congruent. Oh, let's not see. Okay, well, what does that give me? That gives me this angle is congruent to this angle, is congruent to this angle, is congruent to this angle. So all those angles are congruent.
Yes.
I know that this is congruent to that, and this is congruent to that, because this triangle is congruent to that triangle. But I know this is congruent to that, and this is congruent to that, because both these triangles are isosceles triangles. Okay, so that gives me all that. Now looking at just these bottom two triangles. So focusing on the bottom half of this picture now. Looking at these two triangles, the one on the left and the one on the right. Those two triangles now are congruent by side angle side. This side is congruent to itself. That angle is congruent to that angle. This side is congruent to this side. So now these two triangles down here are congruent to each other.
Right.
Which gives me that this angle is congruent to this angle. Since they make a straight angle, I know that that's a right angle and that's a right angle. And furthermore, I now know that this side is the same as this side.
Is that just accepted?
We already handled that.
We did, but he didn't.
No, we're now back to us. We're doing RC constructions in our geometry. So we're building on top of what we have, just putting circles using a definition of a circle. And so, there we have it. This point where the line goes through it is the midpoint. So this line, CD, bisects AB, and it does so perpendicularly. It splits AB in half, and it does so in a perpendicular way. That's what we were trying to do. Construct a perpendicular bisector on AB. So I had AB to start with. My job was to find a perpendicular line that goes right smack through the midpoint. That's what we did.
What were you trying to prove? Refine. That's
If
what.
I give you this segment, AB, your job was to construct a line that goes through the midpoint. So it goes through the midpoint and is perpendicular to the line I gave you.
And that's what you did, right?
And that's what we did right here, CD.
Okay.
It's perpendicular because those are right angles, and it goes through the midpoint since these two sides are congruent to each other. That is congruent to that. So this point right here has to be the midpoint. Okay. So the next one, much easier after we get that one out of the way. The next one, he says, just between A and B. Sorry, not between A and B. Now he says, I give you a line, pick a point on the line anywhere, P, and construct a line perpendicular to P, that intersects at P. How can we do that? I just construct a circle around P. It intersects this line twice, here and here. So call this point A and call this point B. Notice that A and B now are the same distance from P. So now if I use this construction to construct a perpendicular bisector for AB, that's going to go right through P. And so I can create a bisecting line at any point on a line you want. I just find, you pick the point, I find 2 points on either side the same distance away, and construct their perpendicular bisector exactly how we did here. And it will go right through your point, and it'll be perpendicular just like we want.
Perpendicular to one.
Yeah, so this will be now a right angle. I'd redo this.
Couldn't you just draw a line?
We need to know how to construct it. So my pictures up here look ugly, but if I were using these tools, I could construct it very precisely.
I know. Couldn't you just, do you have to draw the full circle to get, because a perpendicular line is
At a right angle.
At a right angle, right?
Yes.
Yes. Couldn't you just draw a line that has a right angle? Or do you have to go through all of
So
this
we
circle?
start out with a line. Now I'm trying to carefully draw a line that's perpendicular to that. I can't just draw it. I know that up here, just drawing seems like it looks good enough. But if we were trying to be as perfect in precision as we can, just drawing is awful. If I go through this construction here, and I did it out carefully, this would get me a line perfectly perpendicular to this line. And going perfectly through the middle.
Well, yeah, for that, but that had 2 points.
So over here, start out again. So here's your problem. I say, here's a point, P. I need you to construct a perpendicular line through P. Perpendicular to this line. Here's your whole setup. What do? I need to find a point on either side of P that's the same distance away from P. So if I construct a circle at P, so I construct my circle at P, then where it intersects here and where it intersects here, those 2 points are going to be the same far away from P. So we call that A and B.
Okay.
Now doing exactly what we did over here, construct a perpendicular bisector, that will go exactly through P, and it will be an exactly right angle.
I'm just wondering, what's the point of the circle? Like, what is the circle here?
The circle here was just so I could find A and B that are the same distance from P. I'm just making so I reset up what we had over here. Over here I had A and B, 2 points equidistant from the midpoint.
I'm just wondering, what does A and B have have to do with the perpendicular line? Why do you
When
have
I constructed this perpendicular bisector, I have this point A and this point B.
I'm saying, yeah, you need A and B to find the midpoint. How does it help you find a perpendicular line?
Because you're gonna do circle
Because
on
I need to do, reconstructing my
Circle on B.
construction over here.
circle on A, circle on B, and then
Create
those
my circle on
circles
B that is A as a radius. Construct my circle at A using B as a radius. Redoing exactly what we have over here.
and then wherever.
So finding
Where those
A,
intersect and
circle
those
B.
intersect, draw the line down, and it turns out that that is a perpendicular bisector. And we finished proving it with this picture.
You just did it with one circle, and I was confused for a second.
Oh,
So finding A and B can help you get those two circles.
So we used one circle to find A and B. Now get rid of that circle. We got A and B. Now we use A and B to construct this perpendicular bisector.
Right.
So the initial circle was just to find A and B. Okay. And then his last construction that he has us do is a bit trickier. He says this time you have a line, and there's a point P up here. I want you to construct a perpendicular line that goes through that point P.
Okay. So you find
Well,
We want to construct a line perpendicular to this line that goes exactly through P. So we got to find the perfect point to kick off from. So if I go straight up, I hit exactly P.
okay, there's another line that goes through P, isn't there? That's not useful.
So yeah, we can start by picking some point down here, call this point A. We could look at AP. So, okay, we got something like that.
well, you could also say there's okay. And you could do that on the other side too, with B, right?
Oh, yeah, we skipped one of his constructions. One of his constructions for copying an angle. But we can copy an angle. So if you
On
give me
one
an
side,
angle, then I can reconstruct that angle anywhere you want. So let's really quick go over that one. Because you're saying we copy this angle down here, right?
I was saying find point B on the line that A is on, just on the other side.
Oh, over here?
Same, no.
Over here.
Yeah, on that line, but same distance from P as A.
Okay, so that might be a point like right here. Here's P
But
there.
yeah, with your logic, you could, because there's a postulate saying if you have an angle, you can copy it on the other side.
So, hold on. If there is an angle up here, I know that there exists some angle down here congruent to it. I know that.
Yeah.
But how do I construct it? Those are two different things. I know it exists. Now, how can I build it? So we're doing two different things. So we're calling these constructions and not theorems. How do you construct this thing? You see the difference in the thinking there?
Yeah.
Okay, so first thing that we need to talk about is copying an angle. So if you have some given angle, here's some given angle A, can I reproduce it on some ray somewhere else? And the question is, what's the construction for that? So let's do that first, and we'll come up and finish this one. Okay. So copying this angle, I'm trying to construct this angle the exact same big over at this point A prime. Doesn't really matter if we have a ray yet. So here's A. My job is to construct an angle exactly that big over here. With me?
Yes.
First thing I do, just create a ray. Doesn't matter which way it's pointing. Right? I can point it that way, doesn't matter. Just start out by creating a ray. All that matters now is how I place my second ray so that my angle is the same big. Right? Okay, so then I'll come over here, and I will just mark off some point B. Doesn't matter. Pick any point B you want. Use this to create a circle centered at A. So it's going to swing down, and we'll get some other point over here. We'll call it C. So this distance and this distance I know are the same big. Now, we already know how to preserve my compass going from one point to another point. So I can mark off the same distance over here. That was the second proof of Euclid's that we did. So I know I can come over here, and I can mark off a C prime, so that this is congruent to this, right?
Right.
This is your compass.
Huh?
You said compass. I didn't say compass.
Sorry. Forget that I said compass. Forget that I said compass.
There exists a point C.
A prime. I can find a point C prime over here, so that this length is the same big as that length. We've already gone over how to do that. When we were doing Euclid's proofs, one of the ones we did is if you have a line in a segment, AB, we showed how you could reconstruct this segment up here, A prime, B prime. So that's the same as that. I think that was our third one with Euclid. Today. We showed how to do that. First we showed how to, if you have a segment and a point, create at this point a segment the same big. So that was the same as that. That was our second proof. Our first one was an equilateral triangle. Our second one was this one. And our third one was now place it on a segment. Too far back?
Yeah, the first one's too far back, but the second one I remember, you create a triangle, but the first one,
All right. You can trust that we already know how to do
Yes.
it. And if I told you to construct it, you can go back to the video and see how to construct it. So we can mark that up. Now I come over here and I create a circle centered at A prime with this as my radius. Now I come over here to C prime and I construct a circle with A prime to A prime as my radius. Those are going to intersect at a point. At that point, I draw the second part of my angle. Now in my construction, by construction, this side is the same big as this side. Oh, and also is the same big as this side. Because those were all radiuses of the same circle. And this is also that way, in the way we constructed it.
okay.
And so now, this triangle is congruent to this triangle by side, side, side. And so this angle is congruent to this angle. Did I do all that right?
Looks like.
No.
Why?
Different argument.
Oh, yeah, you're just trying to find the
No,
angle.
I'm forcing that to be an equilateral triangle, and I cannot say that. I said something weird. Let's reset it. So I've got my angle here. And I mark off point B, and then I can get the point C, so that's the same big as that. Okay.
Yeah.
Over here,
Find point C.
and that's my point A. Over here, A prime.
Point C.
I can again find a point C, so that's the same big. Boy, NLL, trying to keep my picture the same.
Draw a circle with the radius of A.
And then I can draw a circle with the radius of
A.
AC, like that. Oh, and then whatever this length is, okay. So whatever this length is, I come and I draw that circle so it's a different arc, like that. And then we do where they intersect.
What?
So this side is the same big as this side, but this and this are all the same. Okay, that's better.
Oh, you're saying the length of B.
So for this circle, I use this as my radius.
Oh, okay.
So that those two are the same size. And now my side, 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 those two triangles are congruent, and so this angle is congruent to this angle. Okay, now let's go back and prove what his last one was. His last one was, restart the construction. His last one was, if I have a line and a point not on the line, I need to construct a perpendicular line that goes exactly to that point.
Right, okay.
So first, I find some point A down here. A is a point, any point, I don't care what the point is. Looking at this. Now I know how to construct an angle congruent to this angle down here. So I can construct an angle down here so that this is congruent to this, and I can mark off some point P prime so that this is congruent to this.
You draw the P to P prime, P prime to P.
Now P to P prime we can draw in.
Is it perpendicular?
And now we still have to argue that that is in fact a perpendicular bisector.
It's not a bisector, it's just
Or a perpendicular line to the
Well,
here.
by this theorem, side angle
Yeah.
Another option.
This side is congruent to itself, that angle is congruent to that angle, that side is congruent to that side. So these triangles are congruent to each other. And so, this angle is congruent to this angle, and together they make a straight angle. So they're right angles. So this is perpendicular. And it goes through B. So we found it. So once you do the perpendicular bisector and argue how that's the case, the rest of these are not so bad. So that was all of the constructions. Which gets us to chapter 8, parallel lines. And now we get our last postulate. And our last postulate is almost the exact same as Euclid's.
Postulate.
Our last postulate of geometry. For planar geometry.
Wow.
Don't worry, we're mostly just going to talk history now, not a lot of proofs. So your brains can kind of relax now. Okay. So, our last postulate is, let me just ask you a question. I give you a line right here. And I give you a point not on the line.
Okay.
I ask you, how many lines can you draw through that point such that the two lines never intersect? One and only one, right? Okay, that is our last postulate.
Same thing.
You're trying to prove that?
And you might be tempted to think, shouldn't we be able to prove that? Now it seems like it's obviously the case that there's only one line I can draw through that point, so that these two lines never intersect. So shouldn't I be able to prove that? Do we really need that as a postulate?
Why is there only one point?
No. Given a line and a point not on the line, there's only one line I can draw through the given point, such that the two lines never intersect.
Yes.
And it's exactly, it's not how Euclid worded it, but it's the exact same thing Euclid had as his fifth postulate. And most people think that he put off listing that for so long because he kept trying to prove it from these other things. There has got to be a way that I can prove that this is actually the case, and we don't need it as a postulate. And so this is Euclid's fifth postulate. Euclid's fifth is a very famous postulate in history. If you were talking to any mathematician, and you said, well, think about Euclid's fifth, they instantly know what you're talking about. You're talking about Euclid's fifth postulate. Because a lot of mathematicians through a lot of history tried to prove that this could somehow be deduced from these things. It seems like it obviously has to be the case in our geometry. Why can't we prove this thing? Why do we have to take it as a postulate?
Well, you can prove it, can you? Because you can say, by way of contradiction.
And then see if you can get a contradiction. People tried it.
What?
People tried everything left and right. So many man hours went into trying to prove this stupid thing to be true. And then we had a man by the name of Carl Friedrich Gauss, typically referred to as just Gauss, who, for the first time, demonstrated that actually, based on our geometry, that doesn't have to be the case. And that in our geometry so far, it is actually possible that if we have a line and a point not on the line, so far in our geometry, it's possible that there are two or more. If there's more than one, it turns out there's infinitely many. But possible that there's more than one line I can draw through the given point, such that they never intersect.
They will intersect.
Such that they never intersect this line.
How?
So,
Intersect.
Gauss,
Because lines go
hold
down
on,
forever.
hold on. So Gauss
One point,
showed
one line.
that we can set up a geometry where we say there's only one. And he also showed that we can set up a geometry where there's more than one. And it turns out that you have to have it as a postulate and you can't prove it. And this postulate is what determines how our space kind of bends. So up until now, the other geometry that we're going to be talking about is called hyperbolic geometry. So right now we're at a crossroads. Are we doing planar geometry or are we doing hyperbolic geometry? If we choose a postulate where there's only one line through a given point such that they never intersect, then we're doing planar geometry, sometimes called Euclidean geometry. If we accept it as our postulate, actually there's more than one, now we are in the realm of hyperbolic geometry. And so what is hyperbolic geometry versus Euclidean geometry, versus planar geometry? And let me give you some intuition for this. So first off, let's think about a saddle on a horse.
Okay.
So roughly
Saddle.
drawing, a horse's saddle looks like this.
Yes.
From a side view.
Yes.
From a bird's eye view, now looking down on it, it's just going to be a rectangle. Perfect bird's eye view.
Wait a second. That's looking at how. Where's the horse?
This is looking at the side of the saddle. The horse is facing that way. There's a saddle going over a horse.
Okay, there's a little bit, but not that much.
It's been exaggerated for the sake of seeing the curvature.
Okay.
Okay. So now, I want you to think about, on the saddle, think about, let's draw 2 lines. We'll do the green lines first, from a bird's eye view. Think about those green lines. From a bird's eye view, those 2 green lines, they don't intersect, right? Those are parallel lines,
Yes.
Right.
drawn on the saddle. But now, I want you to think about, so if we had them, we could only see one of the lines on the saddle. One of them would be right here. The other one's on the other side. You can't see it
Yeah.
from the side view.
Right.
This is from the bird's eye view.
Right.
Now, think about this distance right here compared to this distance right here. Drawing those blue lines, this one right here goes way up and over to the other side. This one right here goes up and over a little bit to the other side and comes back down. This is much longer than this is.
Not from bird's eye.
Well, we have a bird's eye view, so just picture. But in reality, this curve is much longer than this curve.
Correct.
Yeah.
So these 2 lines, if you took the horse's saddle and with its curvature continued it to infinity. So it has that curvature. It's not flat like a plane, but it's curved. These 2 green lines would never intersect.
The green lines would never. No.
They're parallel.
Yes.
Yet, this point and this point are closer than this point and this point. Distance does not stay the same between 2 parallel lines.
Is that
In plane geometry, the geometry we know and love, when we have 2 parallel lines, then the distance between them is always preserved.
That's what the definition is.
No. Definition of parallel line is they never intersect. Says nothing about preserving distances.
Oh, so you're saying a parallel line could go like this, except for wait, mine's
It's not a line. In planar geometry, all your parallel lines happen to be equidistant from each other the entire time. Over here in this saddle game that we're playing, then that is not the case.
Yes.
And so I can get infinitely many parallel lines. It would be possible for me to draw one. Over here, it's going to look weird if I try and do the bird's eye view because it's going to have weird curvature. But if I actually drew a line now on the saddle that had a slight tilt to it, ever so slight, like that, it will never get over to the other side because the space between it and its other line is growing faster than it's moving up the saddle. So imagine the saddle keeps curving up like this forever, so it doesn't stall out. It keeps curving up like that, and that keeps curving up like that, forever. Since this green line isn't curving up fast enough, it can never get around to the other side. So it's also parallel to this line. So that other green line that we do that's just slightly slanted, it's also parallel to this line. Because it can never get over that hump to the other side. And once I have 2, I have infinitely many, because any parallel line I draw between them, if I know that this is parallel to it and this is parallel to it, any line I draw between it is also parallel. And so that's how you get infinitely many if you get 2. So we're in now what we call hyperbolic geometry. You're used to treating this space like it's just this flat stuff, and it's just preserving this distance all as we go. And that is a very bold assumption that you're making. And nothing in our geometry has required that. So everything in our geometry that was true on these flat planar surfaces, it turns out was also true on these weird saddle horse surfaces. And now if we're going to continue our development, we got to make a choice. Are we on saddle horses, or are we on flat paper?
So hyperbolic is what you would say is geometry in the real world. If you not like if you took an object and tried.
But you're getting onto something. The point is there's tons of weird surfaces. And you can do geometry on any of those weird surfaces.
Okay, can I say one more thing?
Yes.
So two parallel lines are the same distance from each other. Correct.
No. In our space. So when we do planar geometry, yes. In our three-dimensional universe here, yes. Well, kind of. Two parallel planes are.
They are not the same distance.
In this hyperbolic geometry, it's not the case. This hyperbolic geometry, we use a horse's saddle as intuition. What is it really? It's not a horse's saddle. It is this plane that has curvature to it. That goes on forever, curving up.
Yes.
It's not flat.
So are you saying, let's say up here, at the start, no, over here, yes, those two lines are parallel to that straight line?
In plane geometry, these
No.
two are not parallel to this. In hyperbolic geometry, it's very much possible that these two are both parallel to this.
Wow. Ooh.
So in hyperbolic geometry, you have infinitely many lines parallel to a given line that goes through a given point.
I thought you were gonna give a brain a rest.
Well,
Hurts, man.
no more proofs.
Yeah.
Now we just get to talk fun stuff.
Yeah, that's actually awesome.
And so this was absolutely mind-blowing to the world. So Gauss, I told you, was the first one who did this, but he never published. The reason he didn't publish is because there being hyperbolic geometries that human beings can reason about. You probably heard a man by the name of Immanuel Kant. Never heard that name? Okay.
Immanuel Kant.
Immanuel Kant.
Immanuel Kant. No.
K-A-N-T.
Kant.
Kant, sure.
No, Kant. Never heard of it.
Oh, that's nuts. All right, really famous German philosopher. He's like, after Socrates, Plato, and Aristotle, I would guess that Kant is like the fourth most famous philosopher.
Right.
Maybe I'm wrong. All right, anyways,
We have the great books.
Fourth most famous philosopher?
Immanuel Kant is. It's okay. It's good that you don't know. He's a waste of time.
What,
But
what's the bucket? The vegetable?
I'm guessing you're saying Stephen Hawking parallels? Parallels?
Was
He was a physicist, not a philosopher.
Was-
Those are two very different things.
Was okay. I was just wondering if it was one.
No.
Sure.
Philosophers are people that speculate about all sorts of nonsense. Sometimes it's worthwhile, the vast majority of the time, it's a bunch of nonsense.
Okay.
Immanuel Kant, he's one of these guys. He was a famous German philosopher, and he became a big deal in his day, a superstar. And built into his philosophy is Euclidean geometry. So he's before Hilbert, he's before we made all these notions precise, but he had Euclidean geometry built into his philosophy. Can't really make it make sense to you on the fly right now, but essentially he thought that somehow Euclidean geometry existed as part of the structure of your mind. And so it's not that geometry is true, to Immanuel Kant, it's that you can't help but accept it as true, because you can't possibly think any differently. Now, Carl Friedrich Gauss came along and said, actually, this hyperbolic geometry, it's very different, and I can think about it just fine, thank you very much. Which showed that Immanuel Kant's philosophy, which was a big deal at the time, kind of was wrong. It's wrong. Yeah. Anyways, so he knew that. He's roughly 50 years younger than Kant. So as he's coming up, Kant's a superstar in geometry. He knows that if he publishes this, the headlight's going to be on him. And he doesn't want to be in the spotlight, He doesn't want to be in the spotlight. So unfortunately, he never publishes his work that he had. And it wasn't until Lobachevsky comes along, who, getting the relations here, so there's Gauss. Gauss had a friend. His friend's son is Lobachevsky. So Lobachevsky's a bit younger than Gauss now.
Oh,
So-
it'd be like Uncle Gauss.
Yeah, so it's like, hey, Uncle Gauss, look at what I did.
I have
So-
a question.
Go ahead.
So with Kant, was he saying that the reason you can prove them is because it's built into your brain?
Say the reason you understand it.
It's a lot stupider than that. We're gonna go on a tangent on Kant. Okay, it's not part of the lecture. We'll do the Kant tangent after the lecture, and I'll try and give you
Okay.
a blast through of his thinking and his philosophy. Because you have to know a little bit about the early modern philosophers and the problem that they were stuck on first, and a little bit about Aristotle. Okay,
So Gauss.
but sticking with this for a second. So Lobachevsky was the first one to publish. So Gauss didn't publish because he didn't want to be in the spotlight.
Lobachevsky.
Little nephew, Lobachevsky,
Right.
close enough. He ends up stumbling across this exact same thing. He was working on trying to prove Euclid's fifth. He says, this is absurdly difficult. Why can't I do it? You know what? Maybe it has to be a postulate. And maybe it makes perfect sense to talk about a geometry where there's more than one parallel line. And so he starts developing hyperbolic geometry the same way that Gauss did. And then, since he had a connection with Gauss, he basically said, Uncle Gauss, look at what I did. What do you think? And Uncle Gauss says, yeah, I did that same thing a long time ago. You're on the right track. And so, he's the one that ended up publishing. And that's the first time hyperbolic geometry's come out. Now, there's many more geometries than just these two.
So Lobachevsky just takes the credit for it.
He gets the credit as the first one that published, and there was another guy who basically published the same thing at roughly the same time. It's kind of weird how there's nothing, and then at the same time, a few people all come up with the idea at the same time.
How do people know it was Gauss?
Because Lobachevsky said Uncle Gauss figured this out, right?
So we have his notes and stuff. He just never published it to the public.
Gauss.
Yeah.
Yeah, because he didn't want to.
So we have his journals, we have his notes, we have stuff like that.
He can't have himself in the spotlight.
So he just wanted to avoid the spotlight, so he never made it known to the public what he did. Lobachevsky did the same thing, and then he's the one who made it known to the public.
Okay. Aren't postulates undefined terms? They're not.
Now that's also a lot more precise than the way Euclid thought. We now speak about axiomatic systems much more precisely than what they had here. So Euclid starts out before all this, he gives what he has as definitions, and there's tons of them. I can't remember
What's
how.
the definition of a postulate?
No, postulates don't have definitions. So he starts out with 23 definitions, and then he gives you his postulates, which are the basic assumptions. And then he gives you his common notions. These are carryover to every single field. These belong, if you want to show these things are true, that's the field of logic.
There's no logic.
We just build on top of them our geometry. So he
the
says, here's what I'm building on top of. Here's what I'm assuming to be true for my geometry. And it turns out if you swap this one out and you replace it with, okay, we got a line and a point and we have multiple lines that I can draw through that point parallel to this line. That's the only difference in going from this to hyperbolic geometry. You only have to swap out one postulate. It's amazing.
How though? How is it? How are they parallel? Because of the saddle?
Because they never intersect. It's a saddle thing. The space between the lines grows faster than the lines curve towards each other.
The only reason you
It's like we put me and you on a little bit of an angle. So I'm taking a step. Every time I take a step, I get a little bit closer towards you.
Okay.
You just keep walking a straight line. But as I take a step, the classroom between us also grows. So even though I take a step towards you, the space between us has grown.
It's growing, so.
And so this line is moving up the saddle slowly, but the saddle is getting taller way faster than it's moving up.
You wouldn't think that because.
And so it will never get close enough. It will never get over the saddle. And so they'll never
We're
touch.
actually getting farther apart than we are getting closer.
Right, so the space is growing between them.
Every time you take a step.
Not strange.
It's very strange. Very hard to get intuition for this stuff. And we actually use hyperbolic geometry in special relativity. Einstein's special theory of relativity very highly relies on using hyperbolic geometry. So tons of use cases. Now, I just want to introduce you to Riemannian geometry. The simplest one there is, we call it elliptical geometry. And that would be the geometry you would do for the surface of the Earth. Now, this geometry, first off, we can't use all these postulates, so it doesn't follow as naturally as hyperbolic geometry does, but just give you intuition for you, this elliptical geometry. So this geometry on the surface of an Earth, surface of a sphere, is the simplest example. So think about like the surface of the Earth.
Okay.
Now, lines in that geometry are what we call great circles on the Earth. So the equator would be a line. Our lines of, longitude, would all be lines because they go completely around the Earth. When you chart a circle, if you were to look on a map, a flat map, and you were watching a flight, the path of a flight between two cities, you notice that if you plot it out on a map, the flight pattern does not look like this. It actually looks more like this.
That's what we did in environmental science.
Yeah.
And the reason it has that curvature is it's following a line. The shortest distance between those 2
A
points.
straight line.
A straight line, sure. A line. Lines are straight.
Well, then you also have the.
And so the way that you chart these flights is you find a great circle between 2 points, or you find a line between 2 points, and then that's the path you take for the flight.
One more time.
I really wish I had something spherical in here. Don't really have anything.
Something spherical with it, or
Huh?
Like a ball.
Like a ball.
I have a basketball in my locker.
Yeah, not worth taking all that time again. Okay, we'll just try and draw pictures and see how it goes here. So, if I'm drawing a picture, and here is one city and here's another city,
Okay.
then the path I would plot as a flight between those would be a great circle around my sphere. So it would be something that is ultimately gives the circumference of my sphere. I'd find the great circle that lines up those 2 points, and then this would be the path I take as a plane. And so when you plot it out flat, it's going to look curved like this rather than straight. Because you distort space when you lay it out flat. The same way you distort space on like a world map when you lay it out. Notice how on a world map, Greenland looks like it's bigger than all of South America?
Yeah.
That's very much not the case. Greenland is much, much, much smaller than that. That's because you're flattening out the map. And so the top part of the map gets really, really stretched out, whereas the bottom stays more consistent. And so Greenland looks massive when it's not even remotely close to that size. I'm not sure how much it's scaled up, but I would guess it's scaled up by something like a factor of 20 or 30.
Oh, wow.
You're saying those maps where the globe is oval?
Where they lay it out flat.
Where's the square?
Huh?
You're saying it's square.
Square or rectangular, but yes, flat.
Rectangle. Like you're saying when it's an oval, it's not like that.
It's still going to be exaggerated, probably. I mean, it's still going to be exaggerated. How distorted it is, you'd have to look at it. I'm not sure how they split it up. Anyways, the point is, a line now is one of these great circle things.
Okay.
It's not straight.
Well, it's straight, sure. That's what we mean by straight. If you plot it out on this flat paper, okay, it's no longer looks straight, but that's because you changed the curvature. You flattened it. The Earth actually has that curvature.
Yeah.
And so a line on that curvature is very different from the line you get when you flatten it out. But now, in this elliptical geometry, notice that there aren't any 2 great circles I can construct that don't intersect. And so now in this geometry, any 2 lines intersect twice. There and there. And so there are no parallel lines in this elliptical geometry. So, one parallel line in planar geometry, infinitely many parallel lines in hyperbolic geometry, no parallel lines in elliptical geometry.
Okay.
Another consequence of this, something that we haven't proved yet.
What about a line that, like,
Try and give you some more intuition. Here's roughly what triangles look like in each of the geometries. In planar geometry, our angle sum is always 180 degrees.
Okay.
In elliptical geometry, if you go draw a triangle from 3 cities on a globe and try drawing it out perfectly straight, you're going to end up with something that looks like this.
oh, like it when
It's going to be curved, and your angle sum is going to be more than 180 degrees.
that's
And
like,
if you try and do it on one of these saddle-looking things, and you look at the angles are going to be less than 180 degrees. And so triangles look very different in these 3 things.
so geometry is very different in these.
The geometry is very different. And so there isn't geometry, there's plane geometry, there's hyperbolic geometry, there's elliptical geometry. There's an infinite number of geometries.
So if you did a line on that globe that doesn't intersect, you try to make one that
Then it's not a line. So you're thinking we have a globe, and we think about our is
So
it
there's-
latitude that goes this way?
Yeah.
We think about our lines of latitude. Those are not lines in our geometry. If we were in elliptical geometry, these would not be lines.
Why?
Why?
One of the properties we want our lines to have is that the shortest distance between any 2 points is along a line.
Wait,
What?
the shorter distance.
We want the shortest distance between any 2 points to be along a line.
Along a line.
Along a line.
Is it a longer line?
Along a line. So that's one property that you naturally want to come out. The shortest distance between this point and this point is not going to be staying, keeping your latitude the exact same, and just changing your longitude. It's going to be something more like this. And this path, it turns out, is going to be much shorter than this path. And so you want, right, it makes more sense if I could show you on a globe and actually draw these points and see the shortest point between them.
You're saying it's shorter on the
The red path is the shortest path. Something like it.
shortest path compared to the line it's on? Or shortest
That is the line it's on. This is not a line. This is a curve.
Why can't it? Why?
Because it doesn't satisfy the properties of being a line. We're not developing elliptical geometry, so I can't show you how this violates the postulates of elliptical geometry. I'm trying to give you intuition. Intuitively, one of the things we want our lines to have is that if I have 2 points, and I somehow connect them with the shortest path between them, then the path I connected them with is a line segment. We want that to be true in all our geometries.
So there is no possible way to get a parallel line in
An elliptical geometry.
what?
You just said it exactly right. There are no parallel lines. So planar geometry, there's always one. Hyperbolic geometry, there's always infinite. Elliptical geometry, there's zilch. There are no parallel lines. And so it changes the geometry that we're talking about. And so let me draw out a picture one more time to really try and cement everything in your head, big picture, what it is that we're doing. So, foundationally, drawn this picture out a lot, but it's crucial that you get it. We have logic. On top of logic, we built set theory. It's the most basic field of mathematics. And now, on top of that,
So which set of geometry do we use?
we can be over here doing plane geometry, or we can do hyperbolic geometry.
Or elliptical, right?
Yeah, or there's more. There's lots of fields of mathematics. These are just 2 fields. I'm just trying to show you what presupposes what. So both of them use logic, both of them use set theory, and then you have plane geometry and hyperbolic geometry. And in fact, they even have a lot in common. Everything we've done up till now has been here. It's been in both. And it's only once we introduce a parallel postulate that we're splitting off and saying, now we're doing things that are only in here and not in here. But everything, the exterior angle is larger than any of the 2 alternate interior angles. That's true in hyperbolic geometry as well.
Do we have anything else in plane geometry than hyperbolic? Or is it just parallel?
It's just that postulate that splits them. They have every other postulate in common. This is the only postulate that splits them. And now, if I use that postulate, this postulate, I'm in here. If I use this postulate, I'm in here. Obviously, we're not developing this, so we're not going to develop that. We're just going to develop this. But just trying to help you see the structure of how all these things tie together.
Well, like you were saying with the triangles, wouldn't angles split them too?
So far we have not proved that an angle sum of a triangle is 180 degrees. We're going to have to use this postulate to do that.
Well, I'm saying angles, so let's say the angle on the top one is 44 degrees. It's 44 degrees.
That angle's 44 degrees.
Yeah, let's just say.
Okay.
Now, which one was the hyperbolic? That one would not be 44 degrees, but it's the same angle, right? That's what you were saying?
No. This is just giving you a feel for what triangles look like, how we picture them.
In the different geometries?
In the different geometries.
Would they all be the same triangle, just in different geometries?
I don't know what it means to be the same, because no, they're not going to be the same triangle. The angle sum on this triangle is going to be 180 degrees. The angle sum on this one is going to be over 180. The angle sum on this one is going to be under. So they're different triangles. This triangle can't exist in this space.
I see.
Just like this triangle can't exist in this space. Because really, this triangle has curvature to it that makes it come up.
Yeah.
And you can't put that in the plane. Because once you put that in the plane, you flatten it out and you get rid of that curving up structure. It doesn't fit there.
Right. Those can't be a line anyways, right? In plane geometry, right?
Oh, these things?
Yeah.
Right, those would be curved. They look curved in plane geometry.
Well, you can.
They're straight on the saddle, but when you try and flatten them out, okay, now they look curved. Because you're trying to flatten them out. It's why the path that planes take, when you look out on a map, it looks curved. It's because you flatten it out. If you zoom down and look down the globe, you can see, oh no, that's a straight line. But when you flatten it out on the map, okay, now it looks curved. So this is flattening it out into our plane geometry, because I have to draw on a plane.
Okay.
So it's a limitation of the surface I'm drawing on. So if I had a sphere I could draw on, drawing this would be real easy, and you would see how I didn't have to do the squared curve thing. I could have just drawn a line down from one, line down from the other, line down from the other. This curvature that you see here comes from the fact that the surface you're drawing on has curvature. So, flat geometry, and then there's different curved geometries. And so, one of the big questions is, what kind of curvature does our space have? Our space, our universe, seems like it's a Euclidean space, a Euclidean three-dimensional space, but a Euclidean space. It seems like there is no curvature to our universe. And that if I had a parallel line here and a parallel line here, they act exactly the way you expect them to act. As long as I got them in the same plane in this universe, then the distance between them would stay the same. And that seems like to be a property of the universe that we're in.
There's different factors of the universe that contradict.
Well, the best guess right now is actually our universe looks closer to this. It just has very slight curvature. Oh wait, no, I think it's positive curvature right now, is what they've been oscillating between these two. I think right now the best guess is that it has positive curvature, so it curves in on itself.
Okay, that brings me probably to my last question. So postulate 5. You cannot prove to me that it's true, but you can't prove to me that it's wrong. So
is it true or is it false? And now we get back to what math says. Back to one of our earliest conversations. I tell you that if all men are mortal and if Socrates is a man, then
Socrates is mortal.
Socrates is mortal. Okay, did I tell you that all men are mortal?
No.
No. Did I tell you that Socrates is a man?
Yes. No.
No. Did I tell you Socrates was mortal? No. I said if all men are mortal and if Socrates is a man, then Socrates is mortal.
Right.
All we ever said was implications. We never said that alpha is true. We never said that beta is true. We said alpha implies beta. That's what's true. This statement is what we're calling true. We never called the alpha true. We never called the beta true. We say the fact that alpha entails beta is what's true.
Well, yeah, we did
And-
truth tables and everything.
No, that's if.
I'm saying when we do a proof, in deductive reasoning says the implication is true.
No, when we did those proof tables, the only thing we were calling true and false is alpha can only be true or false. Beta can only be true or false. There's no in between. That's all we.
Yeah, that was something completely different. If you write out a truth table for this, it's not always true. It's only certain special implications that are always true. One of those special implications is, if all men are mortal and if Socrates is a man, then Socrates is mortal. That's an implication that is always true.
Right.
Those are the only kinds of implications we're interested in math. So big picture, what do we have in our mathematical systems? We have axioms or postulates, same things. We never say that those things are true. We look at what they entail. We say if this and this are true, if all men are mortal and if Socrates is a man, Socrates is mortal.
Right.
And so I never said this is true and I never said this is true. I said this entails this. That's what's true.
Right.
Euclidean geometry is not saying that this is true. It's saying these entail everything else that we're saying. That's what's true. It's the implication that's true.
These imply what we're.
Right. I never said that's true. I never said these are our postulates. This is postulate 1, this is postulate 2, this is postulate 3,
Or
this is postulate 4, etc. I never said postulate 1 is true. I said if you have postulate 1 and you have postulate 2, then you have theorem 1.
Theorem 1 is true.
And if you have postulate 2 and you have postulate 3,
Then you have theorem 2.
theorem 2 is true. And it turns out that theorem 1 together with postulate 4
Makes theorem 3.
gives you theorem 3. And you build out this whole web of things.
That's awesome.
We never said that any one of these nodes are true. We said the fact that these imply those and implies all the way up. That's what's true. We call the implication true.
Right.
So we never say all men are mortal. We never say Socrates is man. We never say Socrates is mortal. We say If all men are mortal and if Socrates is a man, then
Socrates.
Socrates is mortal. It's the implication that's true.
Right.
So all mathematical theorems are stated as implications. And we prove that the implication is true. Not the antecedent, not the conclusion, the implication. The fact that the antecedent entails the conclusion. That's what we prove. It's a very subtle distinction. And it's a distinction that made Immanuel Kant go off and make a whole mess of things. It took a long time to make that realization that, oh my goodness, we need to stop saying these things are true. And we need to start viewing math as a field that says, if these are true, then these are true. And it's the implication. That was a very subtle piece of thinking that had to be developed over time. And Gauss is the one who kicked it off by starting to separate these things. So very easy to get confused. And for the majority of history, they were very confused. Because they thought these things are saying things that are facts of reality around us. They didn't view it as geometry. They just viewed it as describing reality.
Right.
And so they said this one's a true one because that's what is in fact reality.
Right.
And it took Gauss to say, whoa, whoa, whoa,
That's
hold
not
up.
true.
Here's one consistent system. Here's another consistent system. There isn't the system of geometry. And so it was a very subtle conversation that kicked off.
So how do they decide which geometry is real?
It's a bad question. What do you mean real?
Which one do you follow? Plane geometry?
Which one do you use?
Yeah.
Depends on what you're trying to do.
So whichever one makes your point best.
Well, in this, so when I'm constructing figures on this whiteboard, then it is very much the case that when I have a line I'm pointing on the line, there's only one line I can draw to the point such that my two lines never intersect. And so if I'm trying to describe what I'm doing in this space, Euclids are far better.
Right.
If I'm now doing geometry on the surface of a globe, elliptical geometry is now far better.
Right.
If I'm now doing special relativity, hyperbolic geometry is now much better.
Okay.
And so it's just a matter of what's the best to use for your case.
Right.
So, it's not that one geometry is right and another's wrong. They're all perfectly right if you understand what they're saying correctly. They're stating a bunch of implications. And the implication's always true.
Right.
Is the antecedent true in this space? Maybe, maybe not. Irrelevant question when it comes to the actual geometry. Very relevant to physicists. And so they spend a lot of time trying to measure the curvature of our universe and see, is it exactly flat? Is it a little bit negative? Or is it a little bit positive? Does our universe somehow curve in on itself? And so that's currently closer to what the current picture is of our universe. Right now, if you could somehow freeze our universe so it's not expanding anymore, would be theoretically possible for you to go that way far enough that you come back around and you're back where you are. Or if we cleared out all the obstacles out of your way, a lot of bad physics I'm about to say, but clear all the obstacles out of your way and give you perfect vision, you can see the back of your own head. Terrible physics, but gets the point, right?
Yeah.
That's what we mean. So that's currently the best picture of our universe, I think. Is it curving in on itself?
Where does the universe stop?
Where does the universe stop?
Yeah, it hurts your brain.
So
Wait a second, no, because
let's talk about how we
this,
think
it's
of the
not
universe.
flat.
So if you want to get comfortable with how we think about the universe, first thing you have to be comfortable with is projecting three-dimensional space down onto two dimensions. So we're going to project you, and we're going to make the universe, and we're going to think about it like the surface of the Earth. So surface of the Earth, and we're going to make us all basically two-dimensional beings on the surface of the Earth.
Okay.
So we make it really, really flat, and all you can see is straight out like that. So you're a being that exists in two dimensions. Draw it out flatly for you, helps you get comfortable with some things.
How flat earthers think about us.
No. Actually think about you two-dimensionally. So here you are a two-dimensional being. Here's your friend.
That's Alvin, that's Julian.
You can't just walk through him, you'd have to walk around him. Think about this. This right here is some contraction in your universe that's able to open and close. We call it a door. You go inside your room and you close the door. Now you have a bunch of friends outside your room. Here they all are. None of them can see you.
But I can see myself and them.
You can't see them. No. If you look out, all you see is a segment.
From here.
You're two-dimensional. Here you are. You're two-dimensional. The only way you can see is that way, that way, that way, that way. You have no concept of out of the whiteboard and no concept of into the whiteboard. These are the only directions you know.
Left, right, up, down.
Left, right, up, or down. Someone says, look out of the whiteboard. What does that mean? You mean this way? No. Oh, so opposite of that, this way? No. Oh, so like combine both of those two this way? No. Oh, the opposite of that? No. Then which way? How do you explain to a two-dimensional being, look out of the board?
You can't. Look up.
Now here's what's crazy. Notice how easy it is for us to see them. Three-dimensional beings looking at a two-dimensional universe, I can see them just fine. He says, how can you see me? Can you see through that wall? No. Can you see through that wall? No. That wall? No. That wall? No. I'm completely enclosed. How can you see me? If I stuck you, and I stuck you in a box in this universe, and there was some four-dimensional being looking at our 3 dimensions of space, they could see you inside the box. Worse than that, they can see inside your mouth. They can see inside your gut. They can see inside your intestines. They can see all inside of you. Which way? That way? That way? That way? That way? That way? No, look out of the whiteboard. Not the ways you're used to pointing. The other way. That's the way I can see into you. So projecting space down into 2 dimensions, it's already quite a leap to do. But now imagine that we are 2-dimensional beings on the surface of this earth. Surface of this ball. You with me?
Yeah.
So here I am, here you are. This is currently the picture of the universe that we use, roughly.
Of the universe.
Of the universe. So I'm at a point in the universe. Now it doesn't make sense to go down inside the ball. And it doesn't make sense to go outside the ball. We exist on the surface of the ball only.
Right.
So the first question is, where is the center of the surface of the ball?
As a 2-dimensional being?
Yeah, you're a 2-dimensional being. Where's the middle of the ball?
Right there.
Right where?
In the center, at the center point. Same.
We're talking about the universe is the surface of the ball. The universe doesn't exist inside the ball. It doesn't exist outside the ball. It's just a surface.
I know.
So where is the center of the universe? You're saying it's not even in the universe? It's the center point of the ball, so it's no part of the surface.
If the universe is 2-dimensional, it's the same length.
So the universe is only the surface of the ball. That's it, right? You're wanting to say that the center is the middle of inside the ball, which isn't a point in the universe. You're trying to say the middle of the universe is a point not in the universe. So if someone says, let's go to the middle of the universe, you say, sorry, the middle of the universe isn't a point in the universe.
What? As a 2-dimensional
Okay, we are on the surface of the earth, and we only know the surface of the earth.
Yes.
That's our whole universe. I say, find the middle of the surface of the earth. Find the center of the surface of the earth. Where do we go? And the concept of center instantly breaks down. There is no center of the surface of the
You're
earth.
saying, as a 2-dimensional being, looking at that picture, that's the universe right there. I can find the center point of that. But now it's a 3D ball. I can't.
Right, we're talking about, sorry, I don't mean this to be a circle. I was trying to draw a 3-dimensional sphere.
Okay.
So this is
I
a
thought
sphere.
You were saying that's a sphere.
Okay.
So, okay.
We are beings on the surface of a sphere.
Yes.
Okay.
Okay.
Someone asks us, where's the center of... They ask us, hey, you can see our whole universe. Where's the center of our universe? And their universe is just the surface of the sphere. What's the answer? Bad question. The surface of a sphere doesn't have a center. You can say, the center is inside the ball. What do you mean inside the ball? You're going to tell me it's a point not in the universe? That's the center of the universe? So the universe has no center. The same way that the surface of the earth has no center. Right? You with me?
I don't know.
You don't know?
The center of the ball is, you stop.
The center of the surface of a ball. Not the center of a ball.
The center of the surface.
We're talking about just the surface.
Wait,
The
the
universe
surface
is
can turn.
just the surface.
Surface can turn though.
A surface can turn.
Yeah, but you can, where's the center of it?
Where's the center?
Yeah.
Okay, so Hopefully now it's clicking into your intuition how it's a bad question. That's why there is no center of our universe. Here's another question that often comes up. Where did the Big Bang happen?
Big what?
The Big Bang. The universe came from the Big Bang, right?
Right.
Where did the Big Bang happen? Did it happen over there? Did it happen over there? Where did the Big Bang happen? So not only is it good to think about our universe as being on the surface of a sphere, but our universe is expanding.
So, the Big Bang Theory is not a good theory.
Let's just
you can't
you're,
prove where
you're,
it happened.
you're jumping way ahead of the gun.
When I get into things that hurt my brain, I want to know.
So, I'm about to make it appeal to you. So the best way to think about our universe is not only the surface of a sphere. Better analogy is the surface of a balloon. And someone is blowing up the balloon.
Yes.
And so it's getting bigger and bigger. So here you and I are standing in the universe. If we just stand there looking at each other, the distance between us is going to get bigger and bigger. It's going to look like we're moving away from each other. Even though we're just standing still. Because the balloon's getting bigger and bigger and bigger, right? That's what we see when we look around our universe. Every galaxy we look at, they all look like they're moving away from us. Now they're not moving away from us, it's that the space between us is growing. And so they look like they're further and further away from us. And notice that it would be possible, if your max speed was 10 miles per hour, how fast you could run, it would be possible that there came a point where I was so far away from you that even if you started running towards me, the space between us would grow so fast you could never actually catch me. Because whoever's blowing up the balloon is blowing it up too fast. And so the space between us grows faster than you can run. Does that make sense?
Yes.
And so that also happens with the speed of light. So there are galaxies out there now that they're so far away from us that light from them can't even get to us. Now some people accidentally say they're moving away from us faster than the speed of light. That's not the case. Space is growing between us so fast that light itself can't travel the distance and will never reach us. And so there's galaxies out there that we'll never see.
Is that why?
So what's the notion of the Big Bang now? The surface of a balloon. We know that the balloon is blowing up. We say, let's run the picture backwards. If it's bigger now, it must have been smaller in the past, and smaller in the past, and smaller in the past, and smaller in the past. So take the balloon now and run it backwards. And so you have the surface of the balloon getting more and more and more and more and more compact. Now we're talking about an infinitely stretchy balloon that can get infinitely small.
So it was nothing.
So it was pretty much nothing. It was so nothing it's absurd to talk about. And someone started blowing it up.
It was nothing, but it was there.
I didn't say it was nothing.
No, I'm saying, yeah. Like,
Okay.
If it gets infinitely small.
Okay, it doesn't get infinitely small. It gets so stupid small, it's dumb to talk about. It gets down to the size of an atom. Okay. So, we got a balloon that can be the size of an atom and someone starts blowing it up. So we run the picture backwards down to the size of an atom. So the whole surface of the balloon was once the size of an atom. So here you are, and you're standing on the surface of the balloon, and you're asking, where did this expansion start?
You know.
Everywhere. Where in the balloon did the balloon start being blown up? The whole balloon.
Everywhere.
Where did the Big Bang happen? It happened everywhere. It's not some explosion that happened somewhere in the universe and things scatter out. It's the whole universe was small and it got bigger.
I'm saying, when did the balloon start being blown up?
Roughly 14 billion years ago.
To us, though. To a different universe out there, it could have been any time. Like, okay.
We know that long ago, roughly 14.5 billion years or whatever it is, that the universe was very small. And now it's the size that it is.
Maybe.
Okay, maybe.
14
maybe
billion years ago, it
14
could've-
billion, not million.
I thought I said billion.
Oh, sorry.
14 billion years ago, there could be a galaxy out there where to them, it's like it is to us right now. But no,
No.
is that no?
We have pictures of the early universe. The same way that I can get a picture of you. How do I get a picture of you? What's the physical process that happens?
Take the camera and take the.
No, think very physically about what goes on. I can see you right now. How can I see you right now? What's happening is there's a photon that comes from some light source. It's going and it hits you, interacts with you. You absorb the photon, re-emit a photon, which then goes into my eye. That's what it means to see you. It's a very physical process.
How do we get a picture of an early universe?
We look at the photons that were emitted by it. It's called the microwave background radiation. Since the Big Bang happened everywhere, then there's photons from it everywhere. See, you're right here, and notice that I could get tens of thousands of people in here, and we could all see you. The ones that I see are a very small selection of the photons that you actually emit. Right? And so to get a picture of you, I only need a fraction of the fraction of the fraction of the photons that actually came off of you. And so early in the universe, with this Big Bang, there was an accompanying explosion, can't get into the physics of it right now, which basically gave off a bunch of photons. And those photons are out in the universe. And so we can look at those photons the same way that you'd look at a picture. And so we can reconstruct a picture of what the early universe looked like in terms of densities. It's very clever stuff. Yeah, there's a lot of physics behind it that we'd have to get into. I'd love to teach you guys some physics if you want to know physics. Physics is a blast.
I
But-
love physics. Doing the homework sounds like it sucks, but learning it.
Physics is a pain. It is a very difficult subject. But it's also far and away one of the most rewarding subjects. Anyways, we went off on quite a tangent. Can end the lecture.